wanted to see what happens if we modify our surface. What happens if we dose some additional atoms from a different material on the surface? And again, we have in this case, it's gallium arsenide nanowire with different crystal structure, different crystal phase. We can zoom in here. So we see here the arsenic atoms in the cubic material. Here's a small insertion of hexagonal structure and cubic again. And then we anneal this surface in an antimony-rich environment. And what we see is that we get incorporation of individual antimony atoms. So these bright spots here, these are antimony atoms, which are seen a bit brighter due to their different size and different electronic properties. And if we count them, we see we have many more of these bright spots in the cubic material here and less of them in the hexagonal material. So it's a factor of 4 higher incorporation in one crystal phase compared to the other. Again, it's the same material. It's only a different ordering of the atoms, which results in a different incorporation of our orders. So it's always they are built into the lattice of the antimony atoms. Here's it's visualized in different color, and this can be explained by surface energies, by the diffusion energy that it takes for an antimony atom to move along the surface until it gets incorporated into a possible lattice site. It was done by density functional theory in the group of Professor Kratzer in the University of Duisburg in Germany. After looking at antimony, we went one periodic table and even went to the even larger atoms of bismuth. We have a similar situation here. So we dose just less than a monolayer of bismuth onto a clean surface of gallium arsenide nanowire. We see here on the cubic structure zinc blende that individual atoms get incorporated here. They are clustering a bit at the edges, but they are at random positions on a clean flat terrace. But if we instead look at the hexagonal part, the wood-side part, we now see that we get in a self-aligned way, or a self-selective way even, that here we, in this crystal phase, we get nice islands or these chains here. So the bismuth atoms now tend to arrange themselves into closed structures, evolving from the step edges here. So the bismuth atoms, the orange one, arsenic, and they are in the same atomic level. It's just that the bonds towards the bismuth are slightly longer. That's why they stick out a bit. And that was proven if we look, zoom deeper in here in the surface. These are, again, all these spots here are arsenic atoms. The few bright spots are bismuth atoms. And you can see here the height difference between them is 50 picometers, so much less than the volume of an atom. So it's atoms which are incorporated in the lattice, that they are just sticking out a bit more since they are larger. Okay, so let's at this point now leave our crystal phase heterostructures and instead go to doping heterostructures. So what we have here is indium nanowires, which are aimed for solar cell application, as I have shown in the motivation. So we have nanowires which at the bottom part are p-doped with zinc, and in the top part are sulfur-doped, or n-doped with sulfur. If we look at them in an SDM image, in this case here, we have the catalytic growth particle that we see strongly, but then we have a rather thin and long nanowire at the surface. If we zoom in and take many spectra here, tunneling spectra, and plot them point by point, so that we see now the density of states at each position here in energy, and do this across the interface, across the PN junction, we can see here, visualize how we get the transition from n-doped Fermi level closer to the conduction band to p-doped Fermi level a bit closer to the valence band. But you can also see it doesn't look strongly doped here. The Fermi level is still within the band gap, and we have here 2 examples of spectra in the n-doped area and the p-doped area. And the potential, the built-in potential, so the shift in energy between them is only 0.5 electron volt. On the other hand, we know the band gap of indium phosphide is 1.3 electron volt, and these structures work as solar cells, where we get an open circuit voltage of 0.9 volts. So we see it's important to look at the surface, because here we have different electronic properties than we have in the bulk, if I can say so, for a 2.5 meter thin structure. So on the inside of the nanowire, we have a larger band gap than what we have here at the surface due to band bending towards the surface. We can look at the same type of structure also with an atomic force microscope, where we just see the topography of such a nanowire, and then also use Kelvin probe mode, where we, in an AFM, probe the surface work function. And even in there, you can see a transition here from the p-doped part to the n-doped part. And if we take a line profile here, we see that, oh, in this case, it's only 0.3 electron volts. It was 0.5 before when we did, you looked at it with scanning tunnel microscopy, only 0.3 with the Kelvin probe here. And that's because Kelvin probe operates in air. So we have the sample is oxidized, we have a humid environment, so we have even stronger bending effects, and the built-in potential at the surface is even smaller as compared to the ultra-high vacuum conditions of the STM. And as an yet additional technique for complementary characterization, we use photoemission spectroscopy and microscopy. It's a special photoemission setup at the synchrotron Electra in Trieste, where the incoming photons are focused into a beam of only roughly 100 nanometer in size. So we can then scan the sample through the beam and look at the electrons which are emitted from our sample. The sample consists here of a single p-n junction indium phosphide nanowire, which is put on two gold contacts with a trench in between. So we're choosing at which element we look now. We get element-specific contrast here. If we choose to look at the gold, we can see lighting up here our electrodes shadowed by the nanowire. If we look at phosphorus, we see the wire, or if we look at indium, we see the nanowire. And of course, we also can then take spectra from the nanowires, photoemission spectra at the n-doped part or at the p-doped part. So we can look at the indium or at the phosphorus, and you can see a shift in energy between the n-doped and the p-doped part for both elements. And that is because our core levels that we probe when we do photoemission spectroscopy, they follow the bending of the conduction band and valence band. So we can measure the built-in surface potential here, which is in this case with this technique again amounts to 0.5 electron volt. And why do we put this wire here on the separate contacts? Well, our aim also was to go towards device properties. So we apply now a bias between both contacts and see how the bias drops along the nanowire. So we have our p-n junction bias either in forward or backward configuration. And then we take spectra along the nanowire point for point for point, what the resolution allows of this beamline. And without any applied bias, we can see the inbuilt potential as the shift of the spectra here when we go from n-doped or intrinsic area or the space charge region to the p-doped area. And if we then apply a forward bias, we see that the potential even increases the potential difference. If we have a backward bias, the potential decreases. So we can read out here how locally along the wire the forward-backward potential changes the alignment and where the applied potential drops along these nanostructures. We would like to also use our STM, coming back to our STM lab, for looking at device structures, and not just at prototypes which are easy, or model systems which are easy to look at, but also looking at realistic structures which are made to be used in devices. So the first challenge then is that we need to navigate to a specific area on a large sample. What you see here is SEM images of a large device structure. So we have here something like 2 millimeters, and there's a processed area inside here where we have indium arsenide nanowires. So we zoom in here, we see this part, we see some markers here. We have to zoom in again in this very small area. And then what you see here is that we have laterally grown indium arsenide nanowires on top of an indium phosphide matrix. So this is SEM images. We then we take our STM tip, move along all the markers, try to find these structures, and yes, we got there. We can image them. So these nanowires here, which are grown laterally on the sample between two contacts, we can zoom in on the surface of such a single nanowire, which are about 60 nanometers wide here. And then again, we can take spectra. We can look at the local density of state at individual positions. And we can see here, there's a change of the band gap, there's a change of the density of states as we move along such a single nanowire. So when we are here in the center of the structure, we have the smallest band gap. If we go a bit along the wire, the conduction band, appears at slightly larger energies. And then if we go to the contacts, it's an even larger band gap. That's due to two effects here. One is that we have different materials. So it's in your gallium arsenide, and we have a larger gallium content here at the contacts than we have inside the wire. We have a gradient here, but we also have strain in the wire, which works in the opposite direction. Now, to bring these together, until now we have looked with our STM at nanowires which are just lying on a conductive surface, and in most cases they were just randomly dispersed. So as we said before, we would like to look at nanowire devices, and ideally we would like to do this while they are biased. So while we put a bias across our nanowire heterostructure. If we want to do that, then we of course need to replace our conductive surface with an insulator. Otherwise, we would shorten the device. But if we have an insulating surface here, we cannot use STM anymore. So what we can do, we use what is called Q+, a tuning fork tip. So it's a STM tip here, which is mounted on a tuning fork so that it can be operated both in tapping mode AFM, or it's not tapping mode, it's non-contact AFM operation, or in STM operation. So we start getting an overview here, finding our structure, looking for it in AFM mode. So what you see here is this tiny nanowire and some large gold electrodes, which were defined on it lithographically before. So we see here that's the titanium structure of the electrode. We zoom in, then we have our nanowire, which in this case consists of an axial heterostructure. So we have an indium arsenide part here and a gallium antimonide part there. So this is the SEM image of the structures when they were still grown, these nanowires. So we have an indium arsenide bottom segment, gallium antimonide top segment. And these nanowires are actually grown to act as an Esaki diode or a tunnel diode. So we can measure now in the STM through the contacts that we have here, through the metal contacts, the transport curve, the IV curve of such a device, and see, yes, we get this negative differential conductance. So we actually have a tunnel diode here, which is due to the expected band alignment between the indium arsenide and the gallium antimonide. But if we now switch to STM mode, so once we are on top of our nanowire, we can switch to we know that we are on a conductive ground, so we can switch to STM mode, take SDR spectra, and we see, oh, these our spectra more or less overlap here in energy. So this structure, electronic footprint that we see at the surface would never correspond to a tunnel barrier as we have here. So again, the surface is different than the bulk inside. This was also confirmed by photo emission microscopy and spectroscopy, because we have a surface layer here of quaternary surface layer, which goes along the entire nanowire. But still, we can, with SDS, move our tip along the nanowire from the gallium antimonide part into the indium arsenide part, and we can see here, oh, there's an area, a depletion zone here in the middle, which is while it still works as a tunnel barrier. And then we can apply a bias, and what we plot here is the topography information. So we have the interface between the gallium antimonide, which is slightly larger in diameter, and the indium arsenide, and then we plot the position of the Fermi level at the different areas. And if we don't apply any bias, it's the same potential everywhere. If we now apply a negative bias to the indium arsenide part, we have a sharp drop of the applied potential at the material interface, because this is now where the highest resistance is. If we instead apply a positive bias to the indium arsenide, we have a forward direction for this material junction, and instead the applied bias drops at within the gallium antimonide part, which now has the largest ohmic resistance within this entire circuit. Still, the limitations here in this approach are that we need to have this lithographic context. We need to use these Q+ tips in the AFM mode, which is difficult. So we would like to instead use an approach, use a structure where we can directly use our STM tip. So our next generation of device measurements then add a structure like this, where we take a silicon wafer, and we locally put some insulators on top, put a metal contact again, which can be externally contacted by thin wires, and then we place our nanowires on these metal contacts. So when our STM tip comes now from top, it either sees the semiconductor, or it sees the metal contacts, or it sees the grounded silicon. So it always has some conductive material where it can walk on. And with this structure, we could realize that we applied a bias here, 3-volt source drain bias between the both ends of the gallium arsenide nanowire, and still could get atomic resolution. And furthermore, we could even see an effect called electromigration. So what we see here is again the side facet of a nanowire, gallium arsenide in this case. We have some defects here in the surface. So we imaged it several times again for over 20 minutes, and the surface doesn't change. But if we now apply a source drain bias along the nanowire and image again afterwards, we see that some of the defects now have filled, some steps have slightly moved. So we have a migration of individual atoms here due to the applied bias. And in our latest version of these device structures, we want to be able to deposit a single nanowire between these contacts. So what we do now is that we define these contacts lithographically. Then we come with a nanoprobe, pick off a single nanowire from a gold substrate, take it with the nanoprobe, and deposit it on our electrodes, so that we then really have a device with one nanowire bridging the gap of our two contacts, so that we then can combine IV transport studies through that wire and STM studies along it. And this approach is still what we're still working on right now. There's a PhD student working on this in our STM lab, trying to get some first combined transport and STM studies of this approach. With this, I want to sum up my presentation. I hope that I could give you some glimpses, some impressions of how scanning, tunneling microscopy, and other surface methods can be used to characterize nanostructures, in this case our 3,5 nanowires, where we can compare atomic surface structure with local electronic properties, even about doping and material composition, and even do this on device structures under operation. I want to thank many people who are involved in this. First of all, I want to thank the organizers of this very nice conference workshop for inviting me. I want to thank all our current and former PhD students and postdocs who've contributed to the measurements. Also my colleagues, Anders Mikkelsen in Lund, Chris Palmström in Santa Barbara, where some of the images were taken. We have collaboration partners for theoretical calculations, and a lot of people who grow and process these structures in our collaboration within the NanoLund Center of Nanoscience at Lund University. And with this, I thank you very much for your attention, and I'm open for questions. Thank you.
Thank you very much, Dr. Tim, for this impressive work and amazing presentation. I can see one question in the chat area. Mr. Kamaljit is asking what is the difference between ACM and STM. I think this could have been clarified during your presentation, but just for more clarification to the participants, if you could explain one more time the difference.
Yeah, sure. I'm sorry if that was not getting clear so much in the presentation. Well, SEM is the standard technique. Scanning electron microscopy is a standard technique which is in many labs, where you have an electron beam which from far away from the sample is focused on the sample, scanned on the sample, and you look at the backscattered electrons and get an image from the secondary electrons, which can nicely show topography, but not much more than topography. I mean, there are other methods available, yes. There is scanning tunneling microscopy, that is such a scanning probe technique, so where you really are in very close contact to your sample. So you have a few angstrom above the surface, where you move your probe along the surface and measure the tunneling electrons. So with that, you are again sensitive to topography, but you're here only sensitive to the surface structure. There is scanning electron microscopy, probes an entire structure that you see. Here we only get our signal from the topmost 1, 2, 3 atomic layers, and we can look at the density or local density of states as well.
Thank you very much, Dr. Tim, for your presentation. I enjoyed this very much, and I think the participants will share my opinion too. There is one question from Biswab Hussain Dal. He is asked, an ion transport study through a nanotube. How can I engineer my device in silicon SiN so that only one tube will be inside the hole?
mean, these engineering things they of course are a bit tricky. So of course you need a good possibilities for lithographic processing, that you can define your structures and prepare, but that's the same what you need for a lot of nano devices. And then in our case, you will use a nano probe within a scanning electron microscope, so very, very thin needle, so to say, with which we can pick our nanowire, move it from the growth substrate and put it onto the prepared device structure. And this, other people do this as well for making nanowire devices. It is even possible, not in the scanning electron microscope, but under a very good optical microscope. But that is a bit more, one needs more experience to do that. But that is possible just with a nanomechanical or micromechanical manipulator, that you pick these structures and place them carefully on a different area.
Thank you, Dr. Tim. There is one more question from Lavata. She's asking how selectively transfer nanowire on pattern device. Is it not a real application?
Well, what we do here, that is, of course, this type of processing or transfer is not scalable. This we do for our characterization, and we can, since this is time-consuming method, scanning tiny microscopy by itself is very time-consuming, so we can only focus at a few structures that we do. If for the people who want to make devices out of these nanowires, the ideal way would be to use them on the growth structure, so do all the device processing around the already existing nanostructures. If you want to transfer them, you can do this either, what we do sometimes as mechanical transfer, so that we directly take the growth substrate and break off all the nanostructures on a suitable substrate. You can do it, you can resolve them in liquid and disperse them. You can try to directly grow them in what is called aerotaxy, grow the nanowires in a vapor, not on a substrate, but just in a vapor flow, and then place them on a suitable substrate directly after growth. So there are different ways how to do that.
Thank you, Dr. Tim. I will want to, there is one more question. How about contact resistance? Epitaxial growth is not possible.
Yeah, contact resistance is an issue whenever you take off these structures, break them off, and put them on a different substrate, and also if you do lithographic contacts on top, that is definitely an issue. That's also why we try to avoid these lithographic structures and try to look at our nanowires when they are on a directly placed on a suitable material. And there what works best for us is that we use a substrate of the same material as the nanostructure that we want to look at. So if we want to study gallium arsenide nanowires, we place them on gallium arsenide 111 wafers, which is the original growth direction for the growth of this nanostructure. So then we have the best electrical contact also between the structures and the substrate underneath.
Thank you very much for all your replies and your amazing presentation. I will invite all the participants to contact you directly if they have any more questions or they need more clarification. So without further ado, I will move to our next speaker. So Dr. Nagaraj Suryadevara will be our next keynote speaker. He is a lecturer in the School of Bioscience, Faculty of Medicine, Bioscience and Nursing at the Mahsa University in Malaysia. He obtained his bachelor degree in microbiology from Kakatiya University, Warangal, India, and his Master of Science in Biotechnology from Bharathidasan University in Churchipalli in India, and a doctorate in biotechnology in specialization of molecular characterization of multi-resistant Pseudomonas fluorescens from turmeric fields of Uttar Pradesh in India, from Bharathidasan University, Tamil Nadu in India. During 2019 and 2020, his contributions were appreciated by receiving various reputable awards, including Best Biotechnologist in 2020, the Junior Best Scientist, and Best Young Scientist, and the Young Scientists from various organizations. Congratulations on the award and wishing you more in the future. I give you the floor to start your presentation. Thank you very much.
Thank you, dear Dr. Donia, for introduction about me. Then I would like to take this opportunity to thank the organizers of the United Research Forum for giving me this opportunity to share my views on applications of nanobiotechnology for the sustainable agriculture. Good morning, good afternoon, good evening, and good night. Various parts of the world, the participants are here. I'm here in Malaysia, it's almost 8 o'clock. Maybe from the London, our moderator is there, it's maybe almost 12 plus. So various parts we are here, okay? Just be patient with me for the 40 to 45 minutes of time. I would like to share on the applications of the nanotechnology for sustainable agriculture. When I go through the topics, so far just now, there is a lot of good informative talks are given by the various well-known researchers. They all talking about the physics. I'm talking about the agriculture, where your physics is implemented here, where your nanotechnology is implemented as an application part in a particular, because you all of you know, the morning I was attended there for the Prof. Nageshwar Rao, something there, one who is given a wonderful talk on it related to the various applications of the nanotechnology. Among these, one particular area, agriculture. Okay, the agriculture, everyone, because we are the human beings, we need to eat the food, right? The apparent struggle of the mankind and animal with environmental issues like the pollution. Today we know that every country facing the issue of the air pollution and the water pollution. Then the food availability, we are getting enough food, but the problem is the food, how good, safe it is. What about the toxins are there, or the heavy metals are there, the chemicals are there. So lot of we believing that we are eating a greeny leafy vegetables, are the vegetables what we are getting from the market, but unfortunately it's full of the pesticides and the fertilizers, which is not at all a recommended dose. Because I'm the fellow came from India basically, so I know the way of agriculture where I came from, the family. The particular dose, the people are not aware about how much dose of the pesticide need to be applied to that particular soil or the particular plant. So automatically the overdosage of these all kind of the toxins, which maybe leads to finally to the breast milk of the mother, is highly toxic. Okay, so when we take a sample of the breast milk from the mother, so we can find there is a lot of toxins. Ultimate aim of the nanotechnology in the agriculture. Agriculture has urged scientists to ponder and rethink on the future unhealthy relationship between the agriculture ethics and upcoming human existence and the health. So mainly here we are focusing on the agriculture, how it will be provide the healthy food. Okay, thus concept of agriculture sustainability has been one of the fundamental emphasis for the scientists to better the socio-economic and environmental of this world. So when you think about the agriculture, what is actually the agriculture? Whatever you are doing, the livestock, whatever you are cultivating, it is comes under agriculture. Agriculture is the backbone of most developing countries, which including the India, Malaysia, where we are here. These all the nations are completely dependent on the agriculture, with more than 60% of the population is reliant on it for their livelihood. Source of livelihood and contribution to the national revenue. When you look into the nation Malaysia, here the oil palm industry, which is a big revenue for the country. When you look into the India, the most of the 70 to 80% of the population depend upon the agriculture. Supply of the food as well as the fodder for the animals, and the significance to the international trade marketable surplus, because here the international trade, what we are doing from the various countries to import or export, then the marketable surplus and the foreign exchange resources and the great employment opportunities, and finally the economic development of the individuals and also the nation. So here agriculture takes a great role for the individual's economic life. What is the importance of this sustainability? What is actually the meaning of the sustainability? Sustainability, a stable and a long life for our cultivation, whatever we are doing, frequently encompasses a wide range of production practices, which including conventional and organic. You might be heard about the term everywhere now. The passion is the organic. How certified organic product is it is, whether it have a certification. If it is a yes, what type of the certification is it is, okay? So there is a lot of chemicals and the pesticides are there. A regionally integrated system of plant and animal production practices are designed to produce long-term results. So here, when we look into it, production of the sufficient human food, feed, fiber, and fuel to meet the needs of a sharply rising population. Every country, there is none of the country population is decline. All the population throughout the globe, it is increasing. So we need to provide enough food material to them. Then the protection of the environment, it is a very important thing. You all of you might be aware about this, the COVID-19. Since the last year, almost it's a 1 year, where the first case we found in the Wuhan. Now the entire world take a break. How the break it is, everyone is arrested. Earlier we make a disturbance to the environment. Now a environment take a long break. Now it is a renovating back to normal, and the expansion of the natural resources supply and the sustainment of economic viability of the agriculture system. Systems in agriculture, what way you can be work it on. Here there is a lot of areas we can be focus on it. Soil salinity management, because when you go for the agriculture, we need to know about the minerals and the soil salinity, either it may be acidic or the basic. Okay, then we need to look into it. Energy management, nutrients and the soil fertility management, and the integrated pest management, then the pasture land management, erosion management, post-harvest losses and management, which comes under here in the nanotechnology, how you can manage the post-harvest losses management, and the livestock management, water and irrigation management, fishery, aquaculture, and the wetland management. When it comes to the fishery, aquaponics, how in the aquaponics, how the nanotechnology will help us, we will be see one by one. Actually, it is a basic information what is the nanotechnology, because here I can see a lot of expertises in the nanotechnology, but it's my responsibility to deliver to the audience who are might be have an idea on the nanotech, may not be have. Nanotechnology is the art and science of the manipulating matter at the nanoscale, the design, characterization, production and application of structure, device and system by controlling shape and size at the nanoscale. When you look into a gold as a normal, what its properties, when you turn them into the nanomolecules, how it is. When the graphite outside as a macromolecule, how it responds. When you make it into a nanomolecule, how it will be respond. So always when we look into it, the nano materials have a rigid structure, we have a longevity, and also the toughness. Okay, these all, when you look into a pencil, the pencil have a graphite or the lead, which one is a very delicate one. But when you make it into a nanomolecule that have a very strongest, like a iron or some more bigger than that, it might be have it. In this regard, field of nanotechnology has been majorly useful and potentially associated with promise of effectively contributing to the environmental and the agriculture sustainability. This scientific technology dealing with a manipulation and usage of the various types of materials in the nanoscale, which range from the 1 to 100 nanometer range, has aided the environmental sector with the potential applications of these beneficial nanomaterials possessing unique properties. The advantages of this nanomaterial over the bulk material, as I mentioned just now, at the nanoscale, matter shows these extraordinary properties that are not shown when they are the macromolecules. The surface area, cation exchange capacity, and the ion adsorption complexion, many more functions of the clay would multiply if they are brought into the nanoscale. One of the principal way in which a nanoparticle differs from the bulk material is that a high proportion of the atoms in a nanoparticle are present on the surface. When we look into the applications of the nanotechnology in agriculture, where just now I saw the eminent speaker just before talk about the quantum dots and quantum dots for the staining, the clay nanotubes and nanoscale carriers, then the barcode technology, photocatalyst, biosensor for the agriculture, where it might be help as a enzymatic sensors or the enos in the pest management, then the nanolignocelluloses, where it is helpful here for the waste material from the cotton industry, which might be we make it into a fuel conversion, then the fabricated xylem. Applications of the microfabricated nanoxylem vessels here. Nanotechnology in a microfabricated xylem vessels have been in a emphasis in microbiology and the biotechnological research field, owing it to this particular advancement in nanofabrication. Observational studies on the biological and physiochemical interactions of xylem inhibiting pathogens may be greatly facilitated. So when you apply it, then it will be work against or it's inhibiting the growth of the pathogen. Thus, the studies upon mechanism involved and the pathogenic growth understanding may eventually lead to improve the targeted treatment in agriculture. When you use the nanofiltration for the application of the wastewater treatment, here unfortunately where I came across the leafy vegetables, I love to eat a lot of veggies, but when I came to know that where the cultivation of the leafy vegetables are from the backyard water or the drainage water, how embarrassing the situation, because we all of us are aware that a pinch of a fecal material have a million number of the microorganisms. Where when you are looking into your handphone, you pick a sample, we can see the plenty of microorganisms. When a handphone have this many microorganisms, then what about the drainage water? How much enormous number of the microorganisms are there, which are maybe a pathogenic in nature. So here, the nanotechnology, which might be helped to treat the wastewater before we are applicating for the agriculture sector. Maybe there is a heavy metals are there, there may be a hospital waste is there, so there might be antibiotics are there, antibiotics, maybe the antibiotic resistant microorganism are there. So we need to look into it in the nanofiltration, because I worked here on the multi-drug resistant bacteria since 5 to 6 years we are working on it. We found a lot of multi-drug resistant bacteria from the polluted water or from the poultry industry waste materials and all. So that water is using to cultivate the leafy vegetables. Means just you imagine it, the water which is sprinkled on your leafy vegetables or the vegetables coming into the market, straight away it coming into our, after washing we are using it in our processing. Sometimes you maybe use a salads which maybe you not be cook or anything. If you eat the raw salads and all, what will be happening on it? So here, eco-friendly graphene oxides, dendrimers, then the fullerene-based nanosorbents strengthen the membrane for separation, which increases the selectivity and remediates the pollutants, like by mainly here the ultimate aim of the nanotechnology to do bioremediation, where you are taking place of the remediates the pollutants like antibiotics or the heavy metals in water. Thus we are creating a healthy space for the plantation. Then the photocatalysis and advanced oxidation process, where the titanium dioxide nanoparticles is the most widely used photocatalyst. This exists naturally in the 3 different forms: rutile, anatase, and brochite. Which steps involved here is external diffusion of the reactant to the photocatalyst surface, adsorption of contaminant, reaction of adsorbed organic compound with photoexcited photocatalyst, disabsorption of the reaction products, then the mass transfer of the reaction product to the bulk water, which will help it here for the photosynthesis, the photocatalyst process, where the organic pollutant, which is a harmful, will be turned it into a harmless. Later, it will be go through the process of the chlorophyll, which take the photosynthesis process by uptaking the water. Then intake of the carbon dioxide, finally it will be produce the organic compound. So when you are looking into here, where there is a photocatalyst we are using here, where it will have a organic pollutant in the environment, that organic pollutant, which is a harmful product, will be converted into a harmless. Then later it will be absorbed by the water which is released there, or the carbon dioxide which is entered into the environment. Carbon dioxide intaken by the plant, then the water also intake, then finally it will be produce our product what we are eating today. Either it may be a vegetables or the cereals or whatever it is we are eating, it is from there. Then looking into the application part, applying the nanotechnology in the genetic improvement in agriculture, areas of genetic improvement of the plants, the delivery of the genes and drug molecules to specific sites at the cellular level in the plant and animals. This is the advanced technology in the biotechnology, where we call it as a plant biotechnology or the animal biotechnology, where in the plant biotechnology, there is a possibility you can directly induce the gene of interest to the plants, so where the plants will be express its gene. So we have a method called the gene gun method, where we are using the gold nanoparticles which are coated with the DNA molecules. The DNA will be triggered when you trigger the gun with a bullet which is already loaded with the DNA, and the gold nanoparticle will hit the plant leaf. Then it will be pierced inside the plant leaf. Once the plant leaf receives the gold nanoparticle, that gold nanoparticle already coated with our gene of interest, which I would like to transfer there. If it is a crystalline gene where I want to produce it, the BT cotton, which is the Bacillus thuringiensis based cotton, which is a herbicide resistant or the bollworm resistant plants, if I want to produce the gene of interest which I incorporated there, it will be produce a crystalline protein. That crystalline protein, when the bollworm eat that leaf materials, the midgut epithelial cells of the bollworm will be die. Then finally that animal will be, the bollworm will be die. So it can be managed in the pest management through the genetic improvements, through the nanotechnology, which help us to transfer the genetic information. Then the nano array based technology for the gene expression in the plants to overcome the stress and development of the sensors. Then protocols for its application in the precision farming. Then the management of the natural resources, early early detection of the pathogens and contaminants in the food products, smart delivery system for the agrochemical like fertilizers and the pesticides. Now the granule system entered. The next is the one where we are using the nano based. In my further slides, I might be show you guys about how the companies are making a marketing on this particular area. Then the nanoparticle controlling the plant diseases like a nanocarbon, nanosilver, nanosilicon, nano-sized silica silver, then the nano aluminum silicate. The guys who are working here on the nanos, so far you guys might be working on the production of this nanoparticle. Maybe please consider about my view here, where your nanocarbons, how it is help it in your agriculture field of application, maybe a biomedical field of application. These are the two which is really required for any nation. If you provide a good health to the people, if you provide a good food to the people, that nation will be grow like anything. So here when you look into the nanocarbons, thermal conductors, these nanotubes also host the unique electrical properties, which is surprisingly strong. Then these carbon nanotubes could not only penetrate into the hard coat of germinating seed, but it also exerted the growth enhancing effect. By using it as a vehicle in the sense it acts as a vector to deliver desired molecule into the seeds during the germination that can protect them from the diseases. So when we are starting the germination of the seed itself, the process of this nanocarbon, where you're producing this nanotechnology through, it will allow them to produce, and it will not have any toxic or inhibiting or adverse effect on the plant. Only what it carries, there is no side effect, only the what it carries only act there, but this carbon won't be do anything there. Then looking into the nanosilver, nanosilver is the most studied and utilized nanoparticle for the biosystem. it has long been known to have then a broad spectrum of antimicrobial activities and a high surface area and a high fraction of surface atom have a high antimicrobial effect. This is very important thing because where it have a high antimicrobial activity or the antimicrobial effect, there is a more adhesive on the bacterial and fungus, hence are better to act as a fungicide. It might be act as a bactericidal, so you can be protect them. There is a study proven that studied the antifungal effectiveness of colloidal nanosilver particle, which is a 1.5 nanometer average diameter, that solution against the rose powdery mildew, which is caused by Sparothec panosa varrosae, okay? And it eliminates unwanted microorganisms in the planter soils and the hydroponic system. Just now I mentioned about the aquaculture, where it is a new trend of growing the plants in a water, which is called the hydroponic system. It is being used as a foliar spray to stop the fungi, molds, and rot and several other plant diseases. Moreover, silver is an excellent plant growth stimulator. It also helps it as a plant growth promoter or a plant growth stimulator. Then looking into the silicon, silicon is known to be absorbed into plants to increase disease resistance and stress resistance. Not only the human beings, now if you ask the human beings in the globe, almost all those who are studying, maybe they also under the stress. Those who are working, 90% of people are under stress. But in the same way, plants also go under stress based on the soil. If it is a salinic soil, the plants undergo the much stress. Where there is a environmental changes, plants meet to this particular stress resistance, we need to be produce it. Then the aqueous silicate solution, it promotes the physiological activity and growth of the plants and induces disease and stress resistance in the plant. Then the PHSNS, which are the porous hollow silica nanoparticles loaded with a validomycin, which is an antibiotic here, work it. Then the effective concentration of the nano silica silver pythium is a fungus which might be caused the rhizome rot disease in the turmeric. Most of the rhizomes which cause rhizome plantation, this pythium causes. So the magnoporthin griseae, colatotrichum, gliosporidis, botrytis, and Rhizoctina solani. These are the different type of the plants. Showed there is 100% of the growth inhibition at 10 ppm of this nano-sized silica silver. Then when you look into the Bacillus subtilis or the Azotobacter crococum or a Rhizobium tropi, Pseudomonas syringae or the Xanthomonas, which are have a 100% growth inhibition at the 100 ppm. But there is a little disadvantage is that they have also reported that chemical injuries caused by a higher concentration of the nano-sized silica silver on the cucumber and the panis plant when they were sprayed with a high concentration of 3200. Nano-sized silica silver, still a new composition of the nano-sized silica silver for the control of various plant diseases. It consists of the nanosilver combined with the silica molecule and water-soluble polymers. They prepared by the exposing a solution including the silver salt, silicate, and a water-soluble polymer to radioactive rays. It shows there is an antifungal activity and control the powdery mildew of pumpkin at 0.3 ppm in both field and a greenhouse effect. Then aluminum silicate nanotubes sprayed on the plant surface are easily picked up in insect hair. Then the insect actively groom and consume pesticide-filled nanotubes. Biologically more active and relatively more environmentally safe pesticides. Then they are the mesophorous silica nanoparticle can deliver DNA and chemical into the plants, thus creating a powerful new tool for targeted delivery into the plant cell. If there is any plant with a well-known disease, we can be deliver our targeted gene, or we can be repair the gene through this system. Then the developed porous silicon nanoparticles particle system, where the spherical in shape, the array of the independent porous channels, it form a honeycomb like the structure. Unique capping strategy where the plant cells have rigid cell wall, hence to penetrate it, they had to modify the surface of particle with a chemical coating. It has been successfully used to introduce the DNA and chemical into the Arabidopsis thaliana, which is a plant. Mostly do the research on it because it is a very easy to cultivate, and the changes can be done easily. Then the tobacco and corn plants. Nanotechnology for the crop biotechnology, where it is in the three-dimensional molecular structure where the DNA crystals can form. Then the crystals have a sticky ends or a small cohesive sequences where we have a DNA. When you cut the DNA, it will be produce a two type of it. One is called the cohesive end, another one called the blunt end. Blunt end is like this, where the stickiness is very little. Where we have a sticky end is like this, where the sticky end or cohesive end, it will be give a cohesiveness or the joint much. Then the lattice-like structure that extends in 6 different directions, which forming three-dimensional crystals. This technique could be applied in improving important crops. When you are using the nanotechnology, the nanoparticles and recycling the agriculture waste, where you have a cotton industry, in the cotton industry, mostly the main product is the fabric or the garment. But still there is a lot of the waste, which we call it as the cellulose or the other fibers, that can be converted into a low valued products, or maybe a cotton balls or the ants can be converted through this. The fertilizer or the pesticide absorbent, they produce 100 nanometer diameter fibers. It can be used as a fertilizer or a pesticide absorbent, where this technique is called it as a electrospinning. These high performance absorbent allow the targeted application at desired time and location, which you have a nanoparticles which is a polymerized in a formation, the metal nanoparticle in a polymer formation, where I have a nano capsule or a nano emulsion, encapsulated the drug, encapsulated the biofertilizer or a biofeticide, which is incorporated into the nanomaterials. When it reaches to there, based on the sensor, if it is a high temperature, that particular will be open. If it is a touch the water, it might be open. If the pH is changed, it will be open. If a pest is there, it will be open. So based on the desired time or the particular location, that particular pesticide absorbents can be open there. There is a lot of nanoparticles are there, which are the emulsions, maybe a capsule. Capsule itself, it will be covered inside. When your seed is germinating, that time only it will be open. Whatever the required for us, it will be helpful to them. Then you maybe do the production of ethanol from the maize feedstock has increased the global price for the maize. Maize, we use it as a, normally the corn, maybe use it as a corn flour or the feedstock for the cultivator, for the cattles or maybe the livestock there. But from here, after you are taking the kernels from that corn, then next we have a cellulosic feedstock are there. They are now regarded as a viable option for the biofuel production. It can be, the nanotechnology can enhance the performance of the enzymes used in the conversion of the cellulose into ethanol. Then once pest or a drought is detected, there would be the automatic adjustment of the pesticide application or irrigation levels. One is the pest, another one is a drought. Where the pest is attacked, then immediately the nanomaterials can be do the sensing. That nano sensing will help us to give the auto spraying of that particular drug. Then if it is a drought condition, The climatic conditions are changed, where it is mentioned about the drought, that the irrigation, where we have a water supply, might be help us to deal that particular thing. Then the nanosensors dispersed in the field can also detect the presence of plant viruses and the level of soil nutrients. It's not really so far away, where the nanosensors will help us for the detect the presence of the plant virus. Actually, you no need to go to a plant doctor or a agriculture scientist to know about what type of the virus it and all, where you have a sensors of that particular virus or a soil nutrient depletion, if there is a depletion of the nutrition or a pH changes, which can be easily sensed by these nanomaterials which are incorporated there in the soil itself. Then nano encapsulated, the encapsulation itself, where it will be give the slow release of the fertilizer, it also have become a trend to save the fertilizer. Because I'm not sure about the other country where my fellow researchers who are here in this webinar, lot of countries, the farmers are not aware about how much dose of fertilizer they are using. They are not aware how much fertilizer really that plant takes. We don't know how much really that plant is uptaking the fertilizer. So we simply use a 200 kgs or a 500 kgs of the fertilizer per 1 hectare. Unfortunately, the plants in that particular hectare required maybe a 40 kgs, where you are using a 200 kgs. Almost 80% of the over usage of the fertilizer, where you can be cost cut, at the same time you can be minimize the environmental pollution. Nano barcodes and a nano processing could be used to monitor the quality of the agriculture produces. Maybe the technology with emerged with a information technology and a nanotechnology, they might be help us here. Then through nanotechnology, there is a possibility to study the plant's regulation of hormones, where it may be auxins or the gibberellins, where it will be help us to induce the root growth and the plant growth. Because here some plants we have maybe a root product have a highly commercial impact, means you can be give the root growth itself. If you want to know the shoot got a highly impact on the medicinal property, you can be improve the shoot growth, because we can be customize a plant to produce, where you have a callus, the callus have a capability to produce the entire plant when you provide these auxins and the gibberellins or the cytokinins. So we can be do it customized through this nanotechnology, which will be help us to do it. Has developed a nanosensor that react with the auxin. It can measure auxin concentration at a particular point using electrical signal. It helps to understand how plant roots adapt to their environment, especially to the marginal soils. Looking to the recent developments, they have a plan to develop a plastic storage bag lined with a nanoparticle, or because the garbage bag which you want to use, where you have already coated with a nanoparticles, that nanoparticles might be act as antibacterials or maybe act as a biodegradables. So it will be help us to do environmental protection. A milk container was designed with a nano pattern antimicrobial coated that help the dairy farmers, because when you look into the dairy industry, there's a problem is with the microbial contamination. When you have an antimicrobial coating, even there is a possibility you can be protect that milk from the microbes. Then the scientists have planned to develop the nano patterned paper sensor to detect the bovine pregnancy, to determine if the cows, when it comes to agriculture, cows also in the part of our agriculture, which will run the dry without milk due to the udder infections or the pregnancy. Then it have many potential applications in variety of fields. Carbon nanotubes can be used to recognize and fight viruses and other pathogens. However, the results of studies in animals have raised concern about the toxicity of the nanoparticles. So far we are talking about all the advantages. When you look into the advantages, there is almost some disadvantages also there, but we need to be balanced which is the best, whether the advantages are high, disadvantages are high, we need to be looking to it, because you are giving it as a nanoparticles. The nanos deposited into the soil, one fine day it will be the macro. But what about the adverse effects of a longer duration? We need to look into it. Nano-engineered enzymes that will allow simple and cost-effective conversion of cellulose from waste plant parts into the ethanol, which is called it as a biofuel production. Then disposal of the rice husk can be used as a source of renewable energy, where the rice husks, by using the thermal energy, or maybe produce it into a biofuel or a energy. A large amount of high quality nanosilicas are used, making other materials, maybe the glass and the concrete. Through nanotechnology can reduce the growing risk of rice husk disposable concerns. Nanosensors and nano-based smart delivery system could help in the efficient use of agriculture natural resources like water, nutrients, and chemical through precision farming. Through the use of these nanomaterials and the GPS with a satellite imaging of the field. Yes, it is also very near time we have it. The GPS based nanomaterial incorporated. Remotely you can be detect the crop pests or the evidence of the stress, such as the drought conditions. What is here? The precision farming has been a long desired goal to maximize the output. That is ultimately crop yields while you are minimizing the input. What is the minimizing input? Mainly where your investment for the farmers are the fertilizers, pesticides, and the herbicide. We need to be reduce it, increase the crop yield automatically. We can be achieve our precision farming through monitoring the environmental variables and applying the targeted action, which help to reduce the agriculture waste and thus keep the environmental pollution minimum, enhance the productivity in the agriculture, very less chance of the pathogen attack. Then there is a challenges. It is a very expensive and developing it can be cost a lot of money. The technology poses risk to the health as well. This can leave a negative impact on the health and industry, and can happen if the coating on the products produced by this technology includes some of the poisonous microparticles. The late how it is, still there is a study need to be done. The other nanoparticles, other kind of the nanoparticles like a silver nanoparticle, aluminum oxide, zinc oxide, okay, which are in the control of the rice weevil and a grassroots disease in the silkworms caused by the Cytophilus oryzae and a baculovirus respectively. Then the copper nanoparticle in soda lime glass powder showed efficient antimicrobial activity against the gram-positive and gram-negative fungi. The electrospinning from the harvesting the cotton to finalizing the fabric, it's made into over 25% of the cotton fiber is lost to the scrap or the waste. Use this technique of this electrospinning to spin the nanofibers from cellulose, a complex carbohydrate composed of glucose units that make up to the 90% of the cotton materials. So this is the method where it is a help for the electrospinning nanofibers from the cellulose, where we will be get a fiber gel, then we can be produce the material of that cotton. Then the nanosensors for the herbicide detection by checking the oxygen level in the soil, nanoscale herbicides using a nanoparticle to attack the seed coating of the weeds, their germination could be stopped. Then sustainable watering of the crops, where in farm areas more than 50% of water loss occur, high evaporation rate decreases the soil fertility, mineral zeolites used to prevent the water loss. This is the company, everyone knows about this Syngenta company, where the agriculture chemical companies like the Monsanto, which is a Monsanto and Syngenta are well known, BASF also have ventured in the developing the nanoparticle pesticide. The world's leading chemical company already sell a number of pesticide emulsions which containing the nanoparticles, nanocapsules, they are already in the market. The The positive side of the nanoparticle pesticide is that far less need to be applied and reducing cost and environmental damage. Can nanoparticle be obtained from the plants? Yes, of course we can. Where the alpha-alpha plants harvest the gold nanoparticles, the alpha-alpha plants were grown in an artificial gold-rich soil at the University of Texas. The plants typically use their roots to extract the nutrients and even heavy metals from the soil. We can be studied through the electron microscopy, X-ray absorption spectroscopy. They may be able to extract the gold nanoparticle from the plant by centrifugation. Advantages of the green nanotechnology, just so far I mentioned, is the green nanotechnology. Controlled release of active substances and increased bioavailability of the entrapped bioactivities, better stability of unstable active ingredients, and excellent biocompatibility. Exclusive property, the occlusive property increase the hydration and hence the increased penetration of the drug. Easy large scale upgradability and applications are versatile. Today's motto, live green, go green, pray for the green. If everything green, our lives will be good. So here I was not able to present a few of the work which is done in the tea plantation by me, but the paper is already in, we sent for the publication, so the data is not yet mentioned here, where we use the soil drenching and the soil application of these nano-based microorganisms, which we used here as a antagons or a biofertilizers, which were given a real good effect in the nanotechnology, especially in the tea plantation. It is capable of being used in agriculture products that protect the plants and monitor the plant growth and detect the disease. These existing applications of nanotechnology in food and agriculture are more oriented to reduce the negative impact of agrochemical product in the environment. The main goal to achieve the nanotechnology commitment and promise in a more systematic and consistent way to establish potent remedial mechanism and enhance the preventive measure in agriculture to ultimately better the agro-food sector in this whole planet. With this, I take this opportunity to thank the organizers for giving me such a wonderful session to meet the various participants from throughout the globe. Thank you for your visit to our nano world. By this time, I take this opportunity to thank my student, Nivashini, who helped me during this session. And also I thank everyone for your patience. Thank you very much.
Thank you for Dr. Nagarja for this excellent presentation. I think the participants and the candidates also shared the same opinion. It was very enlightening. It is also very amazing to see the wide spectrum of application that use nanotechnology and that affects us directly in our daily life. I will move on to the question. I can see one question from TechnoX. They are asking what is the optimum nano size of the particle used for your work?
The 10 nano is an excellent one, which is giving. But some of the data shows when we are using 100 nanometers, which also have a adverse effects. When we look into it, it is a range from the 10 to 100 nanometers.
Thank you very much for your talk and for your reply. I invite all the participants to contact you directly if they have any more questions or they need any clarification. Thank you very much.
Right.
There is one more question, sorry. From
Dr. Ajendra.
The question is, gold particle used in cancer treatment?
Yes, because when it comes to the biomedical applications, when we want to do the drug delivery through the nanotechnology, it will be help us, sure can be use it.
There is one more question. Nowadays, biofloc fish farming is in an alarming situation in Southeast Asia. Is it safe or not to consume the product? And is there any possibility to apply nanotechnology in such farming?
Yes, sure. There we can, as I mentioned just now, the aquaponics, where the aquaponics is a combination of aquaculture and agriculture, where the nanotechnology implies that it will be help us to protect the produce, either it may be a fisheries or it may be a plants. So, but still there is a, at the end of my session, I mentioned that because we are not sure, none of the research is proven currently what is the nano material, because you know when it is a macro, how it is responding, when it is a micro or the nano, how it is responding. When it moved to the 10 years later of the application, still there is a question is that, but still compared with a chemical way, the nanos which is used in a nano level, it will be help us.
Thank you for your reply. One more question from Mr. Akib. He is asking why silver and copper show good antimicrobial properties and not iron or nickel.
When you look into this copper, the ancient self, when you look into our anciency, there is the silver also, but when you look into the iron and nickel, they are not have such antimicrobial property. That is their nature. That is their composition nature, which may not be have that antimicrobial property.
One more question from Mr. Ali Muhammad. He is asking, in the film of environmental polymer and clay nanocomposites, where it can be applied? And thank you.
It can be applied in the environment. In the field of environment, it is a vast area where you can be use it in the sense bioremediation, then the environmental cleanup. Everywhere we have that chances to use these particular nanomaterials.
Thank you. Mr. Daharshini is also asking a question. How silver nanoparticles can be used in agriculture? And could you tell him few applications?
Yeah, when you go through my slides in the presentation, I mentioned about it, where the agriculture science, we are using these nanoparticles, especially in the biofertilizers, if you want to deliver, or the biopesticides you want to deliver, we can be use this technology. And also you can be use it for the monitoring of pesticide managemental we can be do. Yes, surely I can share my email ID, no issue. You can later contact if you have any doubts. Yes, then.
Thank you, Professor. One more question from Dr. Asad. He is asking, can we use nanotechnology to reduce the fish death rate? And what's the method and phenomenon?
Exactly, if you ask me, we are not very familiar with that, but still we can use in that aquaculture.
Thank you very much, Professor, for your amazing talk and for the great information we got from your presentation. Thank you very much.
Thank you, Dr. Wanga, for giving me this opportunity. Thanks to the organizer for a wonderful session. Thank you.
Thank you very much. So I would like to thank the United Research Forum and the conference for allowing me to be the moderator of the session. And my period came to the end, and therefore I give the floor to my colleague, Mr. John Surendran, who will be presenting the next speaker. Thank you very much, and you're welcome for this conversation. Goodbye.
Yeah, and thank you very much, Dr. Dania. It's my pleasure to work with you today. And thank you for accepting as a co-moderator for the morning session. Thank you so much.
Thank you. The pleasure was mine.
Yeah. So without further delay, I would like to introduce our next speaker, Dr. Udandarao Priyanka. So Udandarao Priyanka is a postdoctoral researcher working in IIT's Bioethics Group at School of Natural Sciences, National University of Ireland, Galway, Republic of Ireland. The topic. During her PhD, she was awarded for advanced research and innovation and her internship award funded by Department of Science and Technology, Government of India, University of Nebraska, Lincoln, a doctorate award for Food Institute, and Indo-US Science and Technology for further, she was awarded international travel grant by Department of Science and Technology and Technology Science and Engineering Research Board for the summer course program. The result by Nanotechnology Institute and the Faculty of Mechanical Engineering, Technology Israel Institute of Technology, Israel. She has publications in peer-reviewed research journals, and her research area of interest includes green synthesis of nanoparticles, nanohybrids, and Waste Road Management. And now I'd like to invite Dr. Udandara Priyanka to share her thoughts with the rest of the audience. Please welcome Dr. Udandara Priyanka to share her views. Thank you so much.
Hello everyone. Am I audible?
Yes, we are audible, and I will also glad to introduce Dr. Nagaraja as go ahead with the session chair. Thank you, Dr. Udandara Priyanka. Please go ahead. We are audible, and you can share your screen right now.
Yeah. Hello everyone. My name is Priyanka. Currently, I'm a postdoctoral researcher at NUI Galway. As previous presenters have already told, nanotechnology has several applications in various fields. So my focus is basically in environmental area. So my work basically deals with degradation of different organic pollutants. So I'll first give a brief summary of my doctoral research work, and then I'll go into the present work which I'm doing. So yeah, the main objective was to isolate an endophytic fungi from a medicinal plant, Netodophytis fetida, and to check its tolerance for the zinc sulfide nanoparticles, because my target is to synthesize zinc sulfide nanoparticles. So I had to check the tolerance of this particular fungus, whether it can, at what extent it can tolerate to the metal. And next, synthesize nanoparticles from this particular fungus and use those nanoparticles as catalysts for the degradation of various organic pollutants. Here, I took 3 different class of organic pollutants. It's just to check how my nanoparticles works for the degradation of dyes and commonly used pesticide and very commonly used drug, which is the paracetamol. So for these when they are released into the environment, like if they're in excess, they are toxic to the environment. So these 3 pollutants I considered for my study. So initially for these synthesis, we have gone to like Agumbe forest, that is in the Dakshin Karnataka in India. So we collected the plants, and these plants I've washed with sodium hypochlorite to remove the unnecessary contaminants, and then I've cut this into small pieces and then exposed it to potato dextrose agar. And once I'm exposed it to the agar media, there is a mixed culture started growing, and from that I subcultured and I took the desired fungus for my study. And as I've mentioned, these are endophytic fungi. Endophytic fungi are the fungus which reside inside the plant, in the intracellular tissues of the plant. The reason for choosing this particular plant is it's a medicinal plant, so we assume those properties will be inherited to the nanoparticles, and it will be another green approach. And how this will work for the photocatalysis. That's why we took this particular fungus from this particular plant. And then for the synthesis process, the aspergillus flavus, which is found to be suitable for the zinc sulfide nanoparticle synthesis. For this, taken the spores from this and added to the media containing potato dextrose broth. After 2 days of growth, after 2 to 3 days of growth, I've added the zinc precursor, that is zinc heptahydrate, to the solution. Then this fungal cells, they take up the zinc precursor and they converted this into zinc sulfide nanoparticles. This is the just a confirmation image of TEM analysis. And this is the probable mechanism which we proposed. When the fungal cells are exposed to the metal stress, they tend to exhibit quinone tautomerism, which is the change in the isomers, and it exhibits superoxide dismutase activity. That is, even the pores surrounding the fungal cells, they also tend to open when there is a stress given. So because of the stress and the whatever enzymes present, they all tend to convert this precursor into nanoparticles, and they are released into the environment. In my case, it is an extracellular synthesis of the nanoparticles. So suppose if it's an intracellular, we have to give other heat shock to release the nanoparticles which are formed inside the cells, to release it outside. But in my case, it's an extracellular, so it's automatically formed outside the system. And these nanoparticles, once they are formed, they are used as catalysts for the photocatalysis. I've added this nanoparticles which are formed to the organic pollutants solution, like the methyl orange, methyl violet, and all. In the previous slide, I've mentioned those 3 class of organic pollutants are added with the nanoparticles, and once they are mixed for half an hour to attain an absorption equilibrium, and then they are exposed to the solar light. As you know, in India, the solar light is very abundant, so that's the reason I've chosen solar light. And then and one more thing, this ZNS nanoparticles are active in solar light and UV light. Since solar light is abundant, we choose solar light for the photocatalysis. Once they are exposed to the solar light, the degradation takes place because of the OH radical formation, and these OH radicals cleave the whatever dye or whatever organic pollutants, which has complex structures, they cleave them into smaller organic molecules. So this is the common photocatalysis mechanism, where the electrons will club with the oxygen present in the media, and then they convert into super hydroxyl radicals, and then they are converted into this hydroxyl radicals. This is a general mechanism which I've showed here. And then based on this study, I've concluded that the degradation percent is 87% and 33 and 51 for methyl violet, 2,4-D and para. It's not very high, but we wanted to try in a green approach. That is our main target. And the total organic carbon was 74%, 57% and 45%. The total organic carbon reduction percentage. And these are the papers published on this work. This work is done in NIT Karnataka Surathkal. This is like my PhD work. Now I'll start with the work which I've started here, like in my postdoc. Here it's not exactly extinction. It's nanoparticles, but we are trying to club the nanoparticles with the microbes. Like it's an amalgamation of microbes and nanoparticles, so that the process will take lesser time and the degradation efficiency also will increase. So as we all know that fungal cells are already great absorbers of organic pollutants. Here we try to club both the absorption and photocatalysis methods. Sorry. So here next, coming to the based on the objectives, first we had to find out what is the band gap of the material. So based on the band gap, we have concluded that UVA light source is suitable for the study. So, and another reason for choosing the fungal cells is the fungal cells in literature. It is reported that the fungal cells are I mean they are resistant to UVA light. That is the reason we've chosen fungal cells. And yeah, next coming to the morphological identification. Initially, the chemically synthesized and biologically synthesized. Here we have used both chemically and biologically synthesized nanoparticles for the nanohybrid formation. So this is the morphological identification. After this, for the XRD patterns of these chemically synthesized and biologically synthesized nanoparticles are just to know the XRD patterns. We have done XRD studies. And further, to make the nanohybrids are mixing the nanoparticles with that of the fungal cells. This is the control image. It's just the fungal cell with the hyphae growth. And after adding the nanoparticles to it, you can see the hyphae is not very clear. So we assume that the nanoparticles are taken up by the fungi, and then to confirm their presence, even the EDAX images were taken to check the presence of zinc and sulfide on the fungal cells. And yeah, and see these fungal cells, these nanobiohybrids are like, we have done two studies. One is adsorption, one is photocatalysis. In the adsorption studies, the problem is that it's more time consuming. Fungal cells are able to take up the organic pollutants, but it's taking more time. So here we have for photocatalysis, what we have done is we allowed the nanohybrids to grow in the media for uh, 4 days, and then we use the nanohybrids for the photocatalysis studies, so that the time consumption for the and the efficiency of the system increases. So based on our results, in next slide I'll show you a table. Yeah, these are the different combinations we have done. One is just the chemically synthesized nanoparticles, next is only biologically synthesized nanoparticles, and next is the hybrids. So the nanohybrids showed better efficiency with the biologically synthesized nanoparticles. This may be because this biologically synthesized nanoparticles have more compatibility with the fungal cells compared to the chemically synthesized nanoparticles, and it took 60 minutes, and it showed 98% efficiency for the degradation. And yeah, and the summary of the work is to mainly to integrate fungal cells and zinc sulfide nanoparticles, and further to check their compatibility, whether they can do they are capable of adsorption and photocatalysis. And further, same system, we are trying to change the nanoparticles so that we can do it in the visible light instead of UV light. So we are trying with that and trying with different organic pollutants also. And we are, if it works, and further we plan to do it in a reactor. This is the future work. So yeah, with this I would like to thank my analytical team for helping me with the analysis, and mainly Science Foundation of Ireland for funding this, and United Research Forum especially for giving me an opportunity. Thank you.
A wonderful presentation, Dr. Priyanka. The way today, what is really the motto of this conference, the application part, especially you explained very well to the research community who really need it for this today's requirement, where you are used your nanoparticles to be control the pollution measurements or maybe a environmental aspects. It's really a good presentation.
Thank you, sir.
Thank you so much, Dr. Rudandara, for this informative speech. So I'd like to go on with the next speaker, Dr. Karina Babu Maliakal. Karina B. Maliakal, his Rodani's page research was based on understanding the growth of 34 fifth semiconductor nanowires. During her postdoctoral research, compound nanowire growth was investigated using in-situ transmission electron microscopy at Lund University. Her interest included in situ, TEM, crystal growth, and nanowires. Please welcome Dr. Karina Babu Maliakal to share her thoughts with the audience.
Hi, please give me a minute. Why am I not? So usually in Zoom, there is an option where you optimize screen sharing for video clipping. That's sort of disabled, is it?
Dr. Karina, can you see at the bottom there is a shared screen option?
Yeah, I can see the share screen option. Usually when you like click share screen at the bottom, there are like two options. One is whether you want to share computer sound and another is optimize screen sharing for video clip. I had some video clips. I would have preferred to use optimized screen sharing for video clip, but however, that is not enabled. Is that some settings that you, okay, maybe like I'll just go ahead without it maybe.
Yeah, please.
Okay. So the videos might not show up very like good, but let's see.
Dr. Karina, you might be open a tab, another tab of that particular video. When you click on the share option, you might be find at the bottom, another tabs can be able to play. But I'm not sure whether it's a play with the video or not, but still you can play.
No, I can play the video. It's just that it won't be optimized for videos, which means that the like videos will be actually slowed and will not be good quality. It's not about whether I can play the video or not. I'll surely be able to play the video, but it won't be good quality. That's okay.
Okay.
I mean, that's not the best situation, but let's go with what we have. So usually Zoom does allow you to like go with good video quality, but I think maybe it's also related to how many people there are, or I don't know. Yeah, it's probably some settings. Okay. Yeah, so my name is Karina. I work at Lund University. Before I go to the talk, so you can like place a speaker view at the top right corner, and you will not be like you will not be blocking any data behind it. So in that white box that I've kept, there is where you can adjust and keep your the window for the speaker. Yeah, thank you. Okay, so I'll talk to you about like our investigation about compound semiconductor nanowires inside a TEM. So the basic outline of the talk will be that I'll first tell you about semiconductor nanowire growth. And sorry, I will tell you first about semiconductors. Then I will tell you about nanowires, and then we'll go to the investigation that we did regarding semiconductor nanowire growth. Okay. So first about semiconductors. So they are like a class of material which like all of us are using. Silicon is like one of the most widely used semiconductors, and it is like used in a lot of electronics. Or majority of the electronics that we've seen is basically based on silicon. And there are also like solar cells which can be made of silicon. There's a cousin of silicon, germanium, which is again a group 4 material. That is also a semiconductor. But the issue with silicon and germanium is that these are both indirect band semiconductors, which means that you cannot get light out of silicon or germanium with any reasonable efficiency. But if you make a compound with a group 3 material and combine with a group 5 material, it's called a 3,5 compound. And some of those materials are compounds or semiconductors, and they're like compound semiconductors. So silicon and germanium are elemental semiconductors because it's just an elemental material. Gallium arsenide, for example, or aluminum phosphide, and like those you can call as compound semiconductors. So like these compound semiconductors have at least some of the compound semiconductors has the advantage that it can emit light, and they have direct band gap materials. So you can use it for different applications like making LEDs and lasers. You can also use it for terahertz detection or infrared detection, and also in electronics. Now let me tell you a little bit more about nano wires. In principle, like because this is a nano conference, I don't have to tell you that nanotechnology is like very promising and there are a lot of advantages. So I'll skip that part. So nanowires are essentially like one-dimensional structures with the diameter ranging around like 10 or 100 nanometer, and the length is usually a few micrometers. Now, what are the interesting things about nanowires? One is, of course, miniaturization. Another is like that you can grow metastable crystal phases. What I mean by that is that some materials can be grown when you're growing in the bulk phase, you grow it only in one particular structure. And you can, by growing a nanowire, grow it in a different structure as well. For example, if you try to grow gallium arsenide, it grows in the zinc blende structure, which is basically one kind of a cubic structure. And if you try growing it as nanowires, you might be able to get a woodside structure, which is basically a hexagonal structure. And depending on whether what conditions you are using for the growth, which means that you can control the crystal structure by tuning the growth parameters. This is very interesting. For example, if you want to like make a heterostructure of like say one crystal structure and another crystal structure, these are very interesting if you want to like make quantum dots, for example, inside a nanowire. And the sides of the quantum dot are going to be atomically flat, and hence it can have a lot of very interesting like properties and very clean system. A very advantageous like property of nanowire is that you can easily integrate different materials into the same wire. So you would know that when people are trying to grow films of one material over another material, it usually it is constrained by the lattice mismatch between both these materials. But when you're trying to grow a nanowire, the area where one material and the other material is overlapping is very small, which means that whatever lattice mismatch is there, the strain which is caused by that can be sort of relaxed slightly. So it is so much more easier to integrate different materials. And it's also interesting that we can combine compound semiconductors with silicon if you're trying to grow as nanowires. You can also try to do a three-dimensional control of the nanowire, both in terms of the morphology and in terms of like whether you want quantum bells, quantum dots, and like so on. And of course, like because this is also a nanostructure, there is like you can have very large surface to volume ratio. So let me tell you about like the basic principle of like nanowire growth. Usually the nanowire growth is understood in terms of vapor liquid solid growth, which means that the reactants are supplied in the vapor phase. They get dissolved inside a liquid catalyst particle. And after dissolving, it can like supersaturate the liquid. And after supersaturating, there might be a solid material which precipitates out of the liquid, and it can form one layer of a nanowire. And because like you're continuously supplying gases from the vapor phase, it can continuously dissolve in the liquid and precipitate layer by layer of a nanowire. So if you're trying to grow, for example, gallium arsenide, a compound semiconductor, you need a gallium precursor and an arsenic precursor. So let's, for example, you can like use trimethyl gallium, which is a compound of gallium, and arsine, which is a compound of arsenic. And you can like use these gases or other gases, appropriate gases for growing nanowires. In addition to these materials, you can also in addition to these materials, you also need a catalyst particle, which, for example, can be gold. Most of the nanowires are grown using like gold as a catalyst particle. And you also need to supply like sufficient amount of like heat energy for the reaction to happen. So what happens is if you're supplying trimethyl gallium and arsine, the temperature due to the thermal decomposition, like you can get gallium and arsenic, and these can dissolve inside the gold-based liquid catalyst. So though the overall mechanism is understood on the basis of this vapor liquid solid growth, there are still a lot of open questions. For example, when the nanowire usually is understood to grow layer by layer, one after the other. So when people try to like make theoretical models, they almost assume that the layer completion is an instantaneous process, but it's only the time between one layer and the next layer which takes a very long time. And that is what is limiting the growth rate according to like some papers. But that is in some sense true if you are looking at elemental semiconductors. Like for example, if you're trying to grow silicon nanowires or germanium nanowires, each layer growth is seen to be like sort of instantaneous. But is that true for compound nanowires also is one aspect of what we like to see here. So for studying a lot of details and like getting a much clearer mechanistic understanding about nanowire growth, it will be good if we try to grow the nanowires and watch it while it's growing. So one facility, the facility that we are using for this is an environmental TEM, TEM standing for transmission electron microscopy. You would like know this. So we are using like system where there is a gas precursor like system where we mix the gases and like supply the gases to for growing the nanowires. And like we use a process called MOCVD, metal organic chemical vapor deposition. It's basically the precursor that we are using for growing, say for example, gallium arsenide is trimethyl gallium, which is a metal organic compound, and that is why it's called metal organic chemical vapor CVD. We also have a microscope. So this is an environmental TEM. Environmental TEM is it's actually nothing environmental friendly. That's not why the green box is there. Environmental TEM just means that like near the sample, you can go to a slightly higher pressure than what you would go in a normal TEM. So this is like similar to what the principle of environmental SEM is, that there is differential pumping, and so you can reach a higher pressure near your sample region. We also need to see what is happening. So whether we are growing the wires or not, or like all the in situ observations are done using like computer, and while we are doing it, we watch what's happening and adjust the parameters accordingly. The TEM holder that we use, like in the first side, it looks very similar to a normal TEM holder, but this is slightly, it is like a very specialized holder that we are using. At the back of this TEM holder, you can see that there are gas lines attached to this. So on the TEM, this is how we connect it. So this is the back of the TEM holder, where there are these like tubings, which are flexible tubings attached to the gas lines. And that is through which we supply the gases used for growing the nanowires. Inside this holder, there are capillary tubes running all the way through the length of the tube, through the like holder, and it releases somewhere in like front over here. And the growth is done on a MEMS heating silicon nitride chip, which acts as a substrate. So we take a zoomed in look at the substrate. It has basically a heating coil. It's basically joule heated locally. And there are regions with silicon nitride membranes. And it is these membranes, like there is a thick silicon nitride and also a thin silicon nitride region. And the thin silicon nitride is electron transparent. So if we are growing like nanowires on top of this, we can like still see by like the electrons will still pass through the sample and you can like view it in the TEM. So on these silicon nitride like membranes, we deposit gold nanoparticles for starting the nanowire growth. And we supply the precursor gases. So if I want to like, so the rest of the talk is going to be specifically about gallium arsenide nanowire growth. So I need a gallium supply and an arsenic supply. And just like the example I was telling you before, I will use like trimethyl gallium and arsine as the precursors. So if I supply trimethyl gallium and arsine to the gold particle, there is the gold mixes with the gallium and forms a liquid spherical particle. And let's see what happens if we continue to supply the gases. So this video might not show up like great. Let us see. So what happened is that from the gold gallium particle, nanowire has nucleated and started growing. Let's look at another video, which is like the growth of gallium arsenide, and you can see that there is layers of nanowire, like layers growing inside the nanowire. Here you can also see that there is one crystal structure which grew over here, and it's another crystal structure over here, which is like one of the interesting properties or interesting concepts as far as nanowires is concerned, that you can form metastable crystal phases also inside the nanowire. So this is actually the stable phase, and this one at the bottom is a metastable phase. And one advantage of like doing things in situ and growing is that if we make a mistake, sometimes we get the opportunity to like correct it. So here we were trying to grow a nanowire. We had increased the temperature, and let's see what was happening. So instead of like growing, it started eating the nanowire, and then we decrease the temperature, and then it started growing the nanowire. So now let's look a little bit deeper into the science aspect of it. So we did try to like measure the catalyst composition of the liquid catalyst while it is growing, and we use a method called energy dispersive X-ray spectroscopy, or EDX, which most of you would know. So this for doing this, we used the TEM mode, and we condensed the beam to the front of the catalyst, and we tried to do the EDX. And because the nanowire is also growing, it's during the growth process that we are doing this measurement. So we put the beam in a way that we know where the rim of this catalyst is. And as the nanowire is growing like forward, and it's like the front face is moving, so we adjust the sample stage also so that the beam is always in the front part of the nanowire. Let us take a look at the signal. So like if you ignore the silicon, which is basically from the background film, there is a lot of gold, which is your starting seed particle, and there's a lot of gallium. But there is very little arsenic that you can see inside the signal. If you try to look at what numbers these are, let us look at actually a graph where we have looked at the gallium arsenic and gold content inside the catalyst particle for a few different wires. So we have there is like a lot of gold inside the catalyst, which is not surprising because gold is what we started with. There is like a reasonable amount, or like a roughly like 30% of the catalyst is made up of gallium. And there is a very little amount of arsenic present, and the arsenic present that we are seeing is like sort of below the detection limit. And we should also remember that there is a gallium arsenide nanowire which is sort of close by. So whatever signal that we are seeing could just be from the scattering from the nanowire. Now, if there is so little arsenic inside the catalyst, and if there is so much of gallium inside the liquid, is that going to influence how the nanowire is growing? That's what we are going to check next. So first, let us look at the layer growth of the nanowire that we grew here. It's again a gallium arsenide nanowire with a gold-based catalyst. So there is like one layer growing and there is a waiting time. There's another layer growing and another like waiting time. So one thing that we should note is that the layer growth is happening not as an instantaneous process. Each layer is taking a finite time to grow. Secondly, like what we want to like investigate in the study is how these two time scales. So one time scale, let us call it as the layer completion time, which is once the layer has started, how long does it take to finish? And this layer propagation is happening by a mechanism called step flow. So which is why sometimes we call this as step flow time. So in this talk, we'll refer to this as step flow time, which is basically the time each layer is taking to complete once it has started. There's also a waiting time between one layer and the other layer. So after one layer finishes, how long does it take before the next layer starts? That's what we call the incubation time or the waiting time. Now let us see how we can distinguish what are the factors determining the step flow time and what is the factor determining the incubation time. So in the first experiment, we do a arsine series, and another experiment we do a gallium series. So in the arsine series, we keep gallium and temperature the same, but change only the arsine flux. That's what we'll look at right now. So here we are changing the arsine partial pressure and keeping the checking the step flow time or the layer completion time. Here you see that the layer completion time or the step flow time is decreasing very drastically when you increase the arsine pressure, which gives an indication that the step flow of the layer is limited by the arsenic availability. This is not very surprising because we did see by EDX that there is very little arsenic inside the catalyst particle. So how much ever arsenic atoms are needed to grow the gallium arsenide, one full layer of gallium arsenide, that much is not present inside the catalyst particle, which is why it cannot form instantaneously. So as and when there is more and more arsenic coming into the catalyst particle, it can like then go to the growth interface and grow the gallium arsenide. So when you increase the arsine pressure, you can see that the step flow time becomes like faster. The incubation time or the waiting time, on the other hand, increases slightly with increasing arsine partial pressure. Now let us look at the second set of experiments where we are changing the gallium precursor pressure. So here we see that except for this like very low gallium pressure, that the step flow time or the layer completion time is remaining pretty much the same all throughout. But the incubation time or how fast or how easily a new layer nucleates is decreasing very drastically when you increase the gallium flux, which means that the nucleation of a new layer is actually triggered by the gallium. So this basically is like seen in this graph that gallium, which is the element which is readily miscible in the gold particle, is what is triggering the nucleation of a new layer. So this means that if you you can control the step flow and the incubation time, step flow time and the incubation time separately by controlling either the arsine pressure or the gallium precursor pressure. Now, so if you look at like the gallium arsenide growth is what I was talking to you so far. The crux of the matter is that the arsenic has very low solubility in the gold gallium catalyst, which is why you're able to see that the step flow time is limited by the arsenic, which is the low soluble, less soluble species. And the nucleation time is triggered by gallium, which is the readily miscible species. But if you look at phase diagrams of either gold assisted gallium arsenide or like gold assisted other 3,5 materials, or for that matter, most of the catalysts which are used for growing nanowires and most of the compound semiconductors usually have one material which has like a very less miscible and another which is very highly miscible. For example, like nitrogen, oxygen, sulfur, phosphorus, all these things are going to be very less miscible. And gallium, aluminum, indium, zinc, all these things will be like very highly miscible. So if you're doing aluminum nitride growth, it's all going to be like the similar philosophy that one material mixes very little. You can check that using like phase diagram and theoretical calculations. And if that is the case, you will be able to very likely control the step flow time and the nucleation time independently. So before I summarize like the talk, I will introduce you to the group. So this was a group when we were like doing this particular study. Now the group has like slightly enlarged. These are the guys who are doing the theoretical calculations for the study. I actually haven't shown you the theoretical calculations, thinking that it might take a little bit more time and might take a little extra time to like make you understand. But the like main point is that we did try to do theoretical calculations and it did match with the experimental findings that we have. So the summary of the talk is that, first of all, we measured the catalyst composition during the growth by energy dispersive X-ray spectroscopy. This is actually a very good achievement to start with, because most of the time when nanowire is growing, all the models for getting like the energetics of the model, you need to know what the catalyst composition is, because the catalyst composition determines what the chemical potential of the material is. And most of the time when people want to get some estimate of what the catalyst composition is, they try to do an XC2 measurement. By XC2 measurement, they would grow the nanowires first, then they would cool down the nanowire and then take it to an SEM or a TEM machine and measure the catalyst composition. The issue there is that the catalyst composition during growth can very, very different from the catalyst composition after the cool down, because the catalyst composition measured after the growth can depend on how you were cooling down. So if you were cooling down in an arsine environment, if you're growing gallium arsenide, that means that the gallium concentration would tremendously decrease inside the catalyst particle. So it is very important to do an in situ measurement, and we were able to do the in situ measurement while growing the nanowires, because in a TEM, it is possible, like in our case, only because we are heating the TEM. The heating region is very small. So if at any point, if you want to do an in situ EDX experiment where you're measuring some change in the catalyst or like some change in any of the nano materials that you're studying as a function of temperature, or if you want to do it at a high temperature, then you should keep in mind that we should use very localized heating. If you take a holder where it's like a furnace holder where a very big region is being heated, that will give enough background noise that your EDX detector won't be able to work. So that is like one takeaway for for people who are interested in like doing in situ composition measurement while heating the sample. Yeah, the next point I was saying was that we tried to study the kinetics of the layer growth process. We see that there is a gallium which mixed very easily with the gold, and arsenic which had very little solubility inside the catalyst particle. Due to this, the highly miscible species, which was gallium, triggers the nucleation of a new layer. So if you have high amount of gallium, a precursor supply, then you can like start new layers like very fast. But because there is very little arsenic present inside the catalyst particle, the layer cannot form instantaneously, even though it has started nucleating. It has to wait for getting all that arsenic to make the entire layer. So the step flow will be determined by, or will be limited by, the group 5 species or the group 6 species, but the nucleation will be triggered by the group 3 species or the group 2 species. So that's all what I want to tell you, and thank you. By the way, did you see the video sort of okayish, or where it was like very pixelated? Hello?
Yeah, we can see that. We can see that.
You did see it like sort of okayish, is it?
Yes.
Okay. And were you actually seeing the video, or like, I mean, were you seeing my face? Was my video there?
We can see both.
Oh, I see. In my screen, I can't see. That's why I asked. Okay, thank you. So like, I can take any questions if somebody has.
Yeah, thank you so much, Dr. Karina, for this informative speech. Here is a query from one of the participants for an essay. So he was asking, the nanowave was synthesized by metal organic chemical vapor deposition and mounted through a transmission electron microscope. I mean, how? Is there any machine integrating CVD and TEM together? That is in a single machine.
So it's actually a custom-made machine. So there is an environmental TEM which is from Hitachi, and we asked them to like integrate MOCVD into it. So actually, if you see, it's not the same system. Actually, it is connected, but it's not exactly the same system. But you need some bit of integration between, yeah. So here you see that, so like there are a lot of gas handling systems separate, and there is an environmental TEM separate, but all these things were put together. So actually our group has a lot of experience with MOCVD, not in the TEM, but like MOCVD in a normal conventional system. And we approached a few companies and asked whether you can like put these things together and do the adjustments. Cause like here, the holder I was showing you was a custom-made holder. So like there are things which are like custom-made and adjusted for doing MOCVD inside the TM. It's not a commercially available system, but it was like custom-made for us. And we approached like some high better TEM companies also, but they anyway were like good, awesome companies, and they had a lot of sales anyway. So they didn't want to like spend or waste time on making our system. Hitachi like agreed to like combine these systems and set the lab for us, and we went with them. Yeah.
Thank you. Here is one more question from him. How was the nanowave purified, removing all impurities from precursors?
So we are not actually using any, so the precursors are all like things which are bought with high purity. And inside the lab, we are not doing any extra like cleaning. I don't know if there is a palladium diffuser. So in my earlier lab, when I was doing normal MOCVD without the TM, we had like a palladium diffuser for cleaning the hydrogen. But here we don't have a diffuser, I suspect. I'm not sure. But the gallium, we certainly don't clean it. We buy it with high purity. And so is arsine. That is also bought with high purity. And we don't purify it further. Yeah.
Yeah, here is a question from Abdul Ali Forgi. How to control the length and diameter of the nanowire?
Okay, so the diameter of the nanowire is very much dependent on what gold particle size or what seed particle size you are choosing. So if you start with, so in our case, we are starting with a 30 nanometer diameter gold seed, and then we put in gallium. So at like the conditions that you are growing, you know roughly like how much gallium is there. So you can say that, okay, if there is 30% of gallium mixed into the catalyst, what size that sort of like hemispherical particle will have. So basically, if you want to make a larger diameter wire, you have to start with a larger seed particle. And if you want a smaller or thinner nanowire, you'll have to start with a smaller seed particle. The seed particle diameter won't be exactly same as the nanowire diameter, because seed will be just like gold, for example, and your catalyst is, and seed will be gold and maybe like more or less like spherical, you can say. It's like actually it's not a smooth shape, it's a like faceted shape, right? But if you are trying to like grow a nanowire, the catalyst particle is roughly hemispherical, you can say, and you can use like the volume of the starting particle is related to the volume of that hemispherical particle that you're having. So that can give you some correlation on the diameters, but that you will have so like for getting say 50 nanometer diameter like nanowire, people might not be able to say what exact particle size you have to start with. You will have to do that with trial and error, and it will also depend a little bit on what conditions you are going to do the growth at. And the length of the nanowire is basically dependent on how long you grow it. So it starts like with like a few 3-4 layers maybe of a material, or maybe like roughly 10 or 20 nanometers length is what initially comes out. And then like if you grow it for a longer time, you can like grow a very long nanowire. In our case, actually, so like the length is sort of limited by how much space we have. So like I was showing you these, so like there are these like these membranes that we have, right? So once like this is the only region where we can monitor the growth. So the maximum length we can grow by like looking at this is roughly this. But most of the cases you are not limited by that. But sometimes what happens is if you grow the nanowire for very long, it might just like become too long, and then it won't be like able to stand like vertically on the substrate. It might just become like a hair and might just like fall off. Yeah. Yes.
Yeah, Shweta has a question. If EDX measured in situ vary from the EDX of final product, which is more useful?
She's asking which is more useful.
Right, exactly.
Yeah. So we certainly believe that it's the in situ EDX which is going to be like more useful, because what people want when people try to model the nanowire growth, they are guessing. Earlier they used to guess what would the catalyst composition be, and nobody knows like what the catalyst composition was. So they were using ex situ measurement for guessing what the earlier thing would be, and people know that it is going to be different, but that's all what they could do. But if you can like grow the nanowires inside a like microscope and measure the catalyst particle while it is growing, you can get a more accurate picture of the catalyst composition, and that you can use for modeling the growth itself. So measuring in situ is like technically is going to be like more difficult, but at least for some systems, if there are some people who like volunteers to do this, it will give a much better perspective about things and some input like to theoreticians on what we should look for. Yeah.
Okay, thank you, Dr. Karina. There is a really a wonderful presentation, a masterpiece from the chemistry, where the control of this nucleation and layer growth in these nanowires by layer. Yeah, I believe this talk might be help to our participants. Really, they were very happy with your presentation. All the best for your future endeavors.
Yeah, thanks.
Thank you so much, Dr. Karina. So still more any further queries can be clarified via email. So here we go for the next presenter, Dr. Selvarani from India. Dr. S. Selvarani is an associate professor in geology at Thiagaraja College, affiliated to Madurai Kamaraja University, Madurai, India. She obtained her master's degree in geology from Jairaj Anapakiam College for Women and PhD in Geology from Kamaraj University, Madurai. Dr. S. Selvarani started her career in Thyroid College as a lecturer and currently continuing her teaching journey as an associate professor. Even though her works pass through diversity of hands, she confirms her interest towards nanotechnology. Her current research was focused on nanotoxicology, hereditary cancer. Please welcome Dr. Selvarani to share her thoughts on the title. Thank you so much. Dr. Selvarani, are you there?
Mute. Am I audible, sir?
Yeah,
Hello?
please go. Yes, please go ahead. Yes.
My is clear as visible or not, sir?
So we are not able to see your screen. Yeah. Okay, right now.
Okay,
Yeah.
okay. So, okay. Thanks for the introduction and also for the organizer for providing the opportunity. So let's jump into the my topic that is anti-cancer activity of gold nanoparticles against liver cancer cell. So here the cancer is a disease that happens when abnormal cells grow too quickly and leave a less space for normal cells. So the liver cancer can be classified into two ways. The primary liver cancer. So this is a one that starts in the tissue of our liver. So the most common type of primary liver cancer is called as a hepatocellular carcinoma. And the second liver cancer is a cancer that started in some other place in the body and moved to the liver. This type is also called as a metastatic liver cancer. So this holds high mortality rate in the world compared to other diseases, mainly due to non-availability of diagnosis at the early stage and also the proper treatment at the advanced stage. Current cancer therapies, that is radiation and chemotherapy, have adverse side effects in the cancer individual that lead to death of a majority of the patients. So it was identified that the non-specificity of drugs to the target tissue was the main cause for the side effects. So numerous works have been streamlined to deliver the chemotherapeutic drug. Apart from that, a natural compound is isolated from the medicinal plants. So that is believed to be a promising lead in the development of anti-cancer drugs. So nowadays, a screening of medicinal plants and their active constituents of various biological activities. For example, the anti-cancer, anti-inflammatory, anti-diabetic activities. So that falls as a major interest. So our study aims to synthesize the gold nanoparticles from the Propyta cunensis. So, and to characterize the synthesized gold nanoparticles by using a UV UV spectrometer, FTIR, SEM, EDAX, and DLS. So, and to assess the cytotoxicity, the bioactive compounds. So, this is a flower, the flower of interest for our studies. So, this flower is considered as a special significance in Buddhist culture in Sri Lanka. But in Tamil Nadu, it is called a Nagalingam flower. The Sivalingam shape is visible at the center of the flower, and the snake-shaped pollen is a speciality of this flower, and this flower gives a very good fragrance. So this is rare one, and this is used for Siva Puja. That is for used for worship of Lord Siva. So first, the flower extract of Propyta cunensis So this extract is used as a reducing agent for the synthesis of gold nanoparticles from the aqueous cold chloride solution. So and this is achieved within 20 minutes of incubation in the water bath. And the color of the gold reduced solution gradually transfer from pale yellow to the dark purple. So the change in color from pale yellow to dark yellow, dark purple, that indicates the excitation of surface plasmon resonance. So that is visualized as a evidence of bioreduction. So it is well known that gold nanoparticles exhibit dark purple or red wine color based on the shape and the size of the collider particles of the gold. So such synthesized gold nanoparticles, this is morphologically visualized in a UV spectrum. So we observe the peak at 540-49. That is a characteristic of the gold nanoparticles. So that indicates the formation of the nanoparticles and are polydispersed. So the aqueous flower extract of Propita is this is used to check the presence of the secondary metabolites like carbohydrate, alkaloids, saponins, phenols, tannins, flavonoids, terpenoids, like glycosides, and the polysterols. So so the preliminary screening of for the presence of secondary metabolites shows the presence of carbohydrates, phenols, tannins, alkaloids, and glycosides, and these so the so the FTIR was made in order to identify the possible biomolecules that is responsible for the reduction of gold ions and capping of bio-reduced gold nanoparticles. The FTIR spectrum of aqueous extract of Propita showed a peak at 3412.22. That is OH stretch. That is H bonded the phenols. And C-double-bond-C stretch of alkanes. And this reveals that the excellent anti-cancer activity of gold nanoparticles this is due to the presence of the phytochemical constituents residing in the aqueous extract of Propita. So this was often identified from the presence of the flavonoids, alkaloids in them. So the present study strongly suggests that the gold nanoparticles can be used as a potential anti-cancer drug, and in future it would also be it is carried to study the mode of penetration and suppression of cancer cell line and the regulation of genes of Gaudian cells. And the same analysis of synthesized gold nanoparticles showed the presence of polydispersed spherical gold nanoparticles, and the EDAX image showed the strong signal for the gold atoms and the oxygen, which were prominent form of biomolecules of Propita, and the strong signals obtained around 2.3 kilovolts. And the EDAX analysis showed the presence of strong elemental gold peak and the oxygen peak. The oxygen peak might be due to the presence of biomolecules bound to the surface of the gold nanoparticles. And the DLS was used to measure the particle size in colloidal solution. So the size of the gold nanoparticles was 59.4 nm. The polydisparity index was found to be 0.286. So to check the activity of newly formed gold nanoparticles, this extract that is synthesized gold nanoparticle is it is that the activity is checked against the liver cancer cell lines. So the liver cancer cells were treated with the various concentration of gold nanoparticles for different time periods. So the result indicates the nuclear morphology of dying liver cancer cells due to the gold nanoparticles treatment. So on these effects were dose dependent. So the silver nanoparticles exhibited excellent anti-cancer activity, and the IC50 value falls on 82.39, 83.57, and 78.78 microgram per ml. And this work observed a steady increase in the cell inhibition from 20% to 200 microgram per ml concentration of silver nanoparticles. So the cytotoxicity effect was compared with the compared with the standard anti-cancer drug 5-fluorouracil against liver cancer cell lines, and their LC50 value is observed. So a large number of in vitro studies indicate that this gold nanoparticles are toxic to the mammalian cells, but some studies have shown that gold nanoparticles has the potential to intervene the gene associated with the cell cycle progression. So also induce the DNA damage that result in the that forms an evidence for cytotoxic effect of silver nanoparticles on cell lines rather than the normal cell lines. So whether this biologically synthesized nanoparticles is that induce cell death or not. So this is subjected to MTT as a clear fragmented DNA ladder were observed in the golden nanoparticles treated with the liver cancer cells. Wherein untreated cells that didn't show any prominent DNA ladder on the agarose gel. So the DNA fragmentation assay confirmed the anti-proliferative effect of a golden nanoparticles that is synthesized from the flower extract of Chroopita. The synthesized nanoparticles showed well-defined fragmentation pattern in the cell line. So, whereas the no clear fragmentation pattern is seen in the untreated that is untreated cells. So it is indicated that synthesized nanoparticles having very less or no effect on the normal cells. So a cancer cell is a mutant human cell that differ from normal by its rapid growth of the cell. So the DNA of a rapidly multiplying cancerous cell is more exposed as compared to the normal cells. So this is used for the treatment of cancer. So the data obtained from this study confirms that the gold nanoparticles induce cell death through apoptosis. This is associated with the cellular events have a profound effect on the progression of benign to malignant phenotype, and would be the ideal target for the therapy of various cancer cells. So that's the thing. So any queries?
Very good presentation, Dr. Selvarani, on the anti-cancer properties of that particular plant. Moreover, at the end, your results about the molecular studies, especially the DNA, which is related to the anti-cancer cells, and where you treated with these plant materials. But there is personally, I have a small question on it, expecting to clarify from you, where you used for the FTIR and you found there is a few phytochemicals are there. is there any control you use to find out what type of flavonoids or the terpenoids, whatever it is there?
No, sir. I just check the presence of flavonoids, whether it's a flavonoid or a terpenoid or some other thing.
Whether your
Not
FTIR peaks are matched with any of the components which may be available commercially, or how strongly
no,
you
sir,
can believe,
I didn't check.
how strongly you can believe that peaks are in the range of your flavonoids or alkaloids.
So I referred with some articles, sir. That's so that is near, the result is near to that. So that's only I used that point. That
wonderful work, really, Dr. Selvarani. The thing, particularly that particular area, if you clarify, it's really a excellent job.
Oh, thank you.
Thank you so much, Dr. Selvarani, for this amazing presentation. So if there are any still other more questions for Dr. Selvarani, I will welcome. Thank you. Any further more queries will be emailed. And now I would like to go to the next presenter.
Thank you, sir.
Yeah, thank you so much. And I would like to introduce the next presenter, Ms. Fozane Hazirausila. Ms. Fozane Hazirausila is a postgraduate researcher working on the interactions of nanoparticles at air-liquid interfaces. The areas of interest include surfactants, permeability, wettability, adsorption isotherms, and particles interactions at biosystems. Now, I would like to invite Ms. Fozane to share her views on the topic she preferred. Thank you.
Hello, everyone. Can you hear me?
Yes, we can hear you.
Okay, great. Just a second. Can you see my screen now?
Yes, we can see your screen and hear you as well. Please go ahead.
Okay. Hello again, everyone, and thanks a lot for organizing such a great event. I am Farzana Hajirasuliha, a second-year PhD student in mechanical engineering at Northumbria University, United Kingdom. Today, I'm gonna talk about the effects of titanium dioxide nanoparticles on the wet foams produced by ionic surfactants. A study on air-liquid interfacial properties. Well, as you know, foams are the aggregation of gas bubbles separated from each other by a thin layer of liquid called liquid film. The interfacial properties of the gas and liquid in the structure of the foams are important because a wide range of technologies and industries are dependent on the comprehending and harnessing these interfacial behavior. Enhanced oil recovery, wastewater treatment, food, cosmetics, and pharmaceutical industries are the examples of these applications. In many of them, nanoparticles are also used in combination with surfactants as the surface activagents, which are used as the main foaming agent. Okay. Titanium dioxide, in fact, when we use the nanoparticles, we want to produce foams of the intended strength and stability. So the challenge in using the nanoparticles with surfactants is tuning the strength and the stability. Titanium dioxide is one of the most ubiquitous nanoscale substances which have been widely applied in various fields. In this study, we try to investigate absorption of titanium dioxide nanoparticles at the air-liquid interfaces of the aqueous solutions of two ionic surfactants, CTAP as the cationic surfactants and SDS as the anionic surfactants were used. So the concentration of the nanoparticles was fixed at 0.1 weight percentage, but the concentration of the surfactant solutions were variable from 110-6 molar to 110-1 molar. The methods that were used was surface tension measurement using profile analysis tensiometer and foamability measurement. So in the tensiometry, we used a pendant drop mode in which a droplet was formed at the tip of the capillary, and all of the measurements were conducted in a fixed temperature as 25 degrees of centigrade. And using the profile analysis tensiometer, we are able to control the area of the droplets or the volume of the droplets. So we try to control the area of the droplets as at a constant amount of 25 millimeters square. And about the foamability test, the wet forms of the solutions in presence and absence of nanoparticles were prepared using manual shaking at the rate of 180 shakes per minute. Then the foams and the bubbles one by one were transferred onto the microscope glass slide to be observed and analyzed by the software. So first of all, they investigated the effect of titanium dioxide nanoparticles on the surface tension. As you can see in this figure, the effect of the nanoparticles on the solutions was dependent on the nature of the surfactant. For example, when we use CTAP as a cationic surfactant, as you can see the blue dots, we have achieved the adsorption isotherms. And then we try to use the solutions with the same concentration, but with presence of titanium dioxide nanoparticles. We observed that at low concentrations of CTAP, there was an increase in the surface tension when we added nanoparticles, but at the moderate concentrations and high concentrations of the surfactant, the trend was different, and the surface tension in presence of titanium dioxide nanoparticles was decreased. But in case of SDS, after measuring the surface tension of SDS in water, which you can see as the red dots, when we added titanium dioxide nanoparticles at lower concentration, the trend was just like CTAP in water, but at moderate and high concentrations, even after critical micelle concentration. The surface tension of the solutions containing nanoparticles were increased. So we tried to use the foamability measurements to see what happens, because foamability is also a phenomenon which can be attributed to the surface tension. So we try to use the exact concentration of the surfactant with and without the particles. So in case of CTAP solutions, as you can see, in the low concentrations, well, we do not have any bubble when we have nanoparticles and when we don't have. But in the moderate concentrations, in case of CTAP, we do have bubbles, and just in 510 minus 5 molar and 110 minus 4 molar, we don't have bubbles. But after it, we do have bubbles. But the trend was different in case of SDS. In case of SDS, you can see that we did not have any bubbles until the concentration of 2.5, 10 minus 3 molar. So, which is completely consistent with the results that we got from the surface tension measurement. Using both of these results, we suggested the mechanism of the actions of titanium dioxide nanoparticles in the surfactant solution. So at low concentrations of the surfactant, the increase of the surface tension shows that the surfactant molecules are involving in adsorption onto the nanoparticles in the bulk of the solution. But in the medium concentration of the surfactant and high concentration, the behavior is different based on the nature of the surfactant. In case of CTAP, it seems that because of the hydrophobic interactions of surfactant molecules and nanoparticles, the surfactant molecules are adsorbed onto the nanoparticles, and the hydrophilic anodized crystals of the titanium dioxide nanoparticles are getting partially hydrophobic. So they come to the interface and act like a surface active agent. So it can be said that that's why you can see the decrease of surface tension at moderate concentrations of CTAP. But in case of SDS, more surfactant molecules are involved into adsorption onto the surface, solid surface of the nanoparticles. So it can be also attributed to the electrostatic interactions between the SDS molecules and titanium dioxide nanoparticles. But at higher concentrations, it seems that we do have, because there are not a lot of difference between the changes of the pure solutions and the dispersions, it seems that the bilayers of the surfactant onto the solid surfaces are formed. We also try to investigate the bubble size distribution for both surfactants with and without particles, initially at the initial time after the formation. So as titanium dioxide nanoparticles are probably adsorbed onto the bubble interface in case of CTAP solution, they would prevent bubble coalescence. These partially hydrophobic solid particles join the air-liquid interface of CTAP solutions, decrease the surface tension, and results in foams with smaller bubble size, as you can see. In comparison with SDS solutions, in which the nanoparticles have no participation in the adsorption process at the air-liquid interface. Therefore, it can be considered that the nanoparticles affect the size distribution of the bubbles based on their performance in the bulk solution and at the interface. So as the final conclusion, it should be mentioned that the nature of the surfactant and its concentration in foams containing nanoparticles are important and playing important role as because the interactions are affected by these two parameters. Thanks a lot for your attention, and thank you.
Dear Ms. Farzana, really a good presentation on your titan oxide surfactants and its foamability. When it comes to the foamability and the surfactants, what about the toxicity levels of that surfactants which you use? Maybe in your go through your research, it might be help us to go on the decomposition of materials which are in the environment. But in the same time, what about the toxicity of your biosurfactants or your titanium dioxide surfactants? How it's respond to the nature?
Well, that's a good question, because both SDS and CTAP can be considered at high concentrations, can be considered as toxic materials, but they are also used as, I mean, at the standard concentrations, they are used as a material, just like, for example, in the detergent industries. But to be honest, I'm not sure about the threshold of their toxicity. And for that's really a good question, because we were supposed to suggest it as because if we can control the adsorption of particles at the interface, especially for titanium dioxide nanoparticles, because of its photocatalytic activity, it would be a good industrial application. But as you said, all of the points about the toxicity should be considered. Yeah.
Because when it comes to a biomedical application or maybe a skincare product somewhere, when we are using it about the foamability, what about the toxicity also we need to know. Especially in the biomedical application, we look into that. That's why I asked you that question. Thanks for your response. Then we will look into the chat box, whether there is any questions related to the topic. Currently, no. The session is handed over to the moderator. Thank you.
Thank you.
Thank you so much, Ms. Farzana, for the response, and many thanks to Dr. Nagaraja as well for organizing this session. So, and we would like to move to the next speaker from India, Dr. Mallikarjun Patil. Yes, here we go. Dr. Patil is working as an assistant professor, postgraduate Department of Chemistry, Basaveshwar Science College, Bagalkot, India. His area of interest is membrane-based separation process or nanocomposite polymeric materials, nanotechnology, and adsorbents. He has several national and international patents on his credits and many international reputed journals as well. He has 7 books on his credit. He served as manager, research and development for Reliance Industries Limited. He has worked in Qatar and Cambridge University, United Kingdom. And I would like to request the audience that Dr. Izara Hari Hilal is not available right now. So we are going to replace this talk with Dr. Patil. So please, we welcome Dr. Patil to share his thoughts. Thank you so much.
Thank you very much. Is it my voice is audible, sir?
Yes, yes.
Okay, thank you. And screen is visible, sir? Hello?
Yeah, we are not able to see your presentation slides. Yes, we.
Okay, now it's visible, sir?
Yes, we can see it now, and we can hear you as well. Please go ahead.
Okay, thank you very much, sir. Good afternoon and good evening to all. Today I want to present one of my research paper, and I want to discuss about the metal oxide nanocomposite copolymeric membrane as CO2 capture device. for natural gas. And myself, my brief introduction already professor has been given, and I'm working as an assistant professor at Basaveshwar Science College, Bagalkot. Okay, today I'm going to present. This is my college where I was working, Basaveshwar Science College, Bagalkot, and this year it's celebrating its 75th anniversary. Okay? And the presentation my presentation outline will be like the first I will discuss about the overview of my presentation. Next, basics of few polymeric membranes, how it will be prepared or how it will be cast, especially in my case. And gas separation theory, a brief gas separation theory. Then we will shift into the experimental section. After experimental section, then we will go for the result and discussion. Finally, we will conclude the topic. Okay, in the overview, the first thing I want to discuss about what is membrane-based gas separation. A separation of a non-component mixture into two product streams. It is split into a retentate and a permeate, where the mixture has been put, but it is separated into a retentate as well as permeate through a semi-permeable polymeric membrane. Through a semi-permeable polymeric membrane. Schematically, I want to show you. Let us consider you have a membrane. And at the feed side, you will feed the mixture of a gases. You will feed the mixture of gases. In my case, it's a CO2 and methane. In my case, it's CO2 and methane will feed onto the membrane top. Once we'll feed this mixture of gas onto the membrane top, because of a concentration gradient as well as because of a pressure gradient from top to the bottom. From top to the bottom, there is a separation will take place. Like CO2 rich permeate will come one side and methane rich gas will go another side. CO2 rich gas will goes to the another side. Where the CO2 rich stream is called as permeate stream, and where the remaining residue, which is called as retentate. That in our case, it's a methane. And in our case, especially industrial application, in our research institute, what we'll do is basically we'll perform industrial applications like a CO2 removal from natural gas, volatile organic compound removal from the water, organic solvent dehydration, nitrogen carbon of flue gas separation, in other words, nitrogen air separation, as well as H2N2 separation, hydrogen hydrocarbon separation, and water treatment. All research will be carried out at my research group. Now we'll go in a brief about how we will conduct a single gas permeation. I will discuss the single gas permeation. So single gas permeation typically looks like this. It's a schematic diagram, P&I diagram of a single gas permeation, where it's a comparative study where the one gas will be fixed and its separation ability will be checked, and another gas cylinder will be fixed here, and its separation ability across through the membrane will be checked here. Later we'll compare gas 1 and gas 2. Gas 1 and gas 2. Where here is that there is a feed will be fed onto the membrane chamber. Then later the gas will come to the membrane. It will come in contact with the membrane here. Later there is a permeation will take place. When the permeation will take place, because already this bottom side has been evacuated through vacuum pump. When this permeation will come, then the change in the pressure, initial pressure to the applied pressure, the change in the pressure over a period of a time will be calculated or will be sensed by means of pressure transducer, and it should be recorded in a computer. And this record typically will look like this. See the curve here. See the curve here. There is a straight line. There is a straight line. And this is actually the unit looks like this. And once you will obtain a curve, how do you calculate? It's by a time lag method. Or constant volume variable pressure method. In other words, it's called as constant volume variable pressure method. Like, what are the parameters we calculate? Permeability, time lag, diffusion coefficient, solubility, as well as selectivity. All these parameters we will calculate by using that curve, that experimentally measured curve. Permeability will be calculated using the formula where P is equal to VL divided by A into T naught divided by Pf into T naught T of dP by dt of blank minus dP by dt of lead. And how will you calculate the value of theta? We calculate the value of theta by plotting the curve, that is theta is equal to negative intercept by slope. I will explain this one just in the next slide. How will you determine the theta? And next, diffusion coefficient, that is diffusion coefficient D will be L square, means thickness of the membrane, L square divided by 6 theta, where theta is calculated by time lag method. Always diffusion will be inverse of the theta, that will be 6 times. How it is 6 times? Because it's a thumb rule. It's a thumb rule. And next we'll go for the solubility. Solubility S is equal to permeability. It's a ratio of permeability by diffusion. And next we'll calculate the by taking the value of solubility. Alpha, that is alpha is equal to permeability of a mixture A by permeability of mixture B. Example I want to give you here. See, the membrane polyvinyl acetate titanium nanoparticle embedded polyvinyl acetate, and the gas we use CO2 as well as methane, where a volume of a permeate is 10.5 centimeter cube. Membrane thickness is approximately 55 micrometer. Then feed pressure, it's a constant feed pressure, that is 4 bar. Effective membrane area is 12 centimeters. So by this, the same curve, like in my previous slide, which I have shown, the same slide which we have shown, we have plotted a curve. See here, initially there is an inclination in the curve. Later, it appeared, or it has been come into the straight line. But we are interested in a time lag method. We are interested only on the straight line. This inclination will neglect. Why will neglect? Because at the initial state there is almost null permeation will be there. And later the gradual increase in the pressure at the permeate side. This gradual increase will be in a straight line. It should be a straight line. And so this steady state condition only will consider. The steady state only will consider, and other things will eliminate. And will extrapolate this graph. This graph. Always it should meet at a negative intercept. So as per the standard rule, 1 is equal to Hello, is it my voice is clear, sir? Hello. Hello.
There is the interruption from the another participant. Wajiha Shahid. Wajiha.
Hello, please.
Material science.
Hello, sir. My voice is audible, sir. Hello, is it clear, sir?
Yes, sir. Now clear.
Okay, shall I continue, sir? There is some disturbance, I think.
Yes,
Shall I
please.
continue? Okay. As per the extrapolation of this curve by curve fitting method, the curve will meet at negative intercept. So that curve, where it will meet, that negative intercept will take, will calculate the slope of this particular curve, that y is equal to mc square as per the standard method, and r square is curve fitting is almost 0.99 to come. So then we can calculate theta. theta value. Theta is equal to negative of intercept, where it will meet that negative intercept divided by slope AB by BC. This is extrapolation. Extrapolation. So here, here there is a sample. Actual one sample of our calculation, not sample is actually exactly where we measured, and for easy of convenience, with the same formula, thickness is constant, membrane thickness, and field pressure, effective membrane area, and dP by dt, that is millibar per second, and time like theta we obtain, and temperature it's 18.67 degrees Celsius, because we will perform under the cold condition like in a AC atmosphere. Then by using our standard formula as we discussed earlier, equal to, we will calculate here dP by dt, that the differential of a leak. In our case, there is no leak in the system, hence we will eliminate this concept, eliminate this term, and we have obtained 5.47 barrel of a thing. Then next we will go for the diffusion, and as for absorption in the same manner by putting the values of the obtained results. Please, 1 barrel means it's a 10 to the power minus 10 centimeter cube at standard temperature pressure, centimeter square per second per centimeter Hg. Okay. Next, once our membrane is suitable for this particular separation aspect, then we'll go for the mixed gas separation. In a mixed gas separation, again there is a mixture of a gases and a sweet gas. It's a mixture of a gas and there is a sweet gas will be there. Here, the components like a pressure gauge and again our membrane cell and initial to measure the pressure gauges like a initial pressure and final pressure will be there. Later, it will directly go to the GC, micro gas chromatography, where the separation will be recorded, and we can calculate the micro GC readings. We can directly obtain. It's an automatic system that have been designed. And now we'll go for the experimental system. How we have performed or carried out this synthesis of a membrane. First, we chosen polyvinyl acetate as a base membrane. I think it's a common polymer, polyvinyl acetate, a synthetic resin which prepared by the polymerization of vinyl acetate monomer. In this most important application, polymerization of a vinyl acetate monomer, in its most important application, vinyl acetate serves as a film forming ingredient. Hence, we chosen this as a this as our main base matrix. Result and discussion that what we have did for this one is first we made it in a soluble with a suitable solvent. Then we have incorporated to this titanium dioxide as a filler. The titanium dioxide is a nano in size. Next we'll go to the result and discussion section, where first we have measured the particle size distribution or particle size of a titanium dioxide. The histogram of particle size distribution is shown in the below figure. It will vary size in between approximately average size between it's written as a 20 to 30. It's a 30 to 40. The average if you take 30 to 30 40. Hence we can call as a 35 nanometer. Average particle size of our titanium dioxide is 35 nanometer. And this is the XRD patterns. We have synthesized the titanium dioxide under different conditions or different time zones. Like it's in just an initial stage at 6 hours. This is at 12th hour, 24th hour, and at 72 hours. At 72 hours, the perfect titanium dioxide nanoparticles have been obtained. The titanium dioxide have been prepared by hydrothermal synthesis. And once we have incorporated our titanium dioxide nanoparticle into the polymeric membranes, then plain membrane as well as a modified membranes we have compared by means of analyzing it by scanning electron microscopy. Nanoparticles of titanium dioxide are distributed uniformly at the molecular level in polyvinyl acetate polymer matrix. Particle size of titanium dioxide is ranged from approximately you can call it as a 35 nanometer. See here, this is the plain polyvinyl acetate membrane. There is no surface change. There is a plain membrane, and this is the sorry, this is titanium dioxide actually. This is the nano titanium dioxide incorporated polymeric membrane, and the other scanning electron microscopic images will show. See how perfectly it has been occupied or accumulated on the surface as well as the inside of the polymeric matrix. As we have calculated and I have explained in a previous how we will calculate the permeability as well as the selectivity. So accordingly we have calculated, and this is the tabulated our results. Like a membranes, we have prepared the plain polyvinyl acetate and 0.5% to the base of a polyvinyl acetate membrane, 0.5% titanium dioxide as well as 1% titanium dioxide to the polyvinyl acetate membrane. The permeability in terms of barrier, which has been explained, is the permeability of CO2 and permeability of nitrogen. For a plain polyvinyl acetate, permeability of CO2 will be like 4.5, 43.5, and 54.3. And for nitrogen, it's a 0.2, 0.205, and 0.32 and 0.34 barrier. See how drastically there is a incline. Drastically there is a change. The permeability of CO2 upon addition of a small amount of a nanoparticle has been drastically enhanced the permeability of a carbon dioxide. And next, P alpha is equal to permeability of CO2 by permeability of nitrogen. If we calculate the selectivity for a polyvinyl acetate, in case of for CO2 selectivity, just 22. Upon addition of a very small amount of a nanoparticle like a 0.5% titanium dioxide or 1% titanium dioxide to the base matrix of a polyvinyl acetate, there is a drastic change. There is a selectivity has been changed from 22 to 136, and again it's jumped to the 154. Since selectivity has a unitless quantity, so just will mention just number 22, 136, and 154. In this way, there is a very big amount of a change upon addition of a titanium dioxide to our membrane matrix. So mixed gas permeation, especially helium-free basic components and actual composition as well as the partial pressure difference. These are the few actual governing forces to enhance the permeability. And then flux, permeability, and selectivity will be calculated in this way that we have discussed already. Overall conclusion for my research work is like to develop a facility for the hollow fiber membrane for this one. Right now we are using a plain membrane. In future we need to use a hollow fiber membrane fabrication, and also a spiral wound membrane we need to develop. This is the major challenge. And acknowledgement. Thank you for the financial support by BV Sangha Bhagalpur as well as the PG Department of Chemistry. Administrative support by my college, that is Basaveshwar Science College, Bhagalpur. And my sincere thanks to our professor, Professor T. M. Aminabavi, as well as our beloved chairman, Sri Ashok M. Sajjan sir. So with this, I will complete my discussion. Thank you one and all. Please, if you have any question, please let me know. If you have any question, please let me know.
Thank you, Dr. Mallikarjun Gowda, for your wonderful work, a masterpiece of work done in your lab, shared with our present participants, where you did a beautiful work on the polymeric membrane semi-permeability. There is a lot of industrial applications you mentioned. When it comes to the result part, it's really a good results where I can see where the normal polyvinyl used, and when you use with a 0.5% and 1% of the titanium oxide, the permeability levels, the percentages are increased really from the 4.5 to 54. It's really good, but when it comes to the application part, where exactly you can be using?
So that's why we're trying to, yes sir, I got it. That's why we're trying to make it in a spirally wound membrane, because then only it's commercially feasible. Like right now we are using a flat membrane. flat membrane is just for a laboratory purpose only. So in future, we are trying for the spirally wound as well as a spirally wound membrane. So then we'll check it. Then definitely it will
just a add-on to this, Dr. Mallikarjuna Gowda sir.
Yes, sir.
When it comes to the application part in the biomedical line, where the patients have some disorders, diseases which may not be able to intake of that particular areas, maybe the kidneys or maybe some particular area of the organs. If it is damaged, how your permeability membrane might be helped to recover that patients in an aspect of the medical line? Just I'm asking you.
Yes, sir. It's a very good question and very challenging as well. And lots of researchers are working on it actually. Very basically, if I want to tell you, like presently whatever the membranes available for dialysis, there is a parchment membrane is available in the market. Already people are using, but it's actually practically so far there is no success as for the kidney, the bladder, and other kind of things replacement. But scientists are still trying for this, and in future definitely we will get an artificial kidney and other things using this kind of membrane.
Because your result shows about this titanium where it have a drastic effect. So in the same way, we might be have a dialysis membrane to be replaced. So we no need to be bothered, because the world population, there is a lot of people are worrying about these kidney failures. So then there is a question from the Kotari Srinivas Rao. What is the strength required for the membrane?
Means I didn't got which kind of strength you want to say? Which kind of strength?
Yeah, Dr. Kotari Srinivas, which kind of
strength means there maybe like you are asking like a membrane's feasibility, or because basically we'll go for the membrane's sustainability, but we'll check with the universal testing machine basically. That result I didn't add actually. We have that result.
Okay, there is another question from the MD Farhan. If it is a membrane and permeability, then it is in the filtration, the first application that comes to mind. That is the question.
It's actually, in my case, it's not exactly filtration. You will not call it exactly as a filtration, because our membrane right now it's working on a solution diffusion model. It's a non-porous membrane. It works on solution diffusion. That's why in the beginning of my presentation I told it's because solution diffusion model, because of pressure gradient as well as concentration gradient, it will permeate. My membrane, which have been proven to be CO2 philic actually. It's not methane philic. Methane philic or nitrogen philic, it's CO2 philic. Filtration means there is a big drawback is separation is bulk separation. It's not so pure and it will not achieve that much grade to this one. But definitely the permeability, the flux will increase. Definitely.
Yes, sir. Actually, the permeability is different and the filtration is different. The permeability comes under the selective absorption. It may be when it comes to the osmoregulation, we cannot decide it. The osmoregulation is the one where it is from the lower concentration to the higher concentration, the particles will be more. So entirely different. Filtration is different and the permeability is different.
Yes, sir. Definitely.
Okay, right. Thank you so much, sir. Now I pass on to the moderator for the next step. Thank you.
Thank you very much, sir. Thank you. Thank you.
And many thanks, Dr. Patil, for this informative and insightful speech. Now I would like to thank you, and I would like to go ahead with the next presenter, Mr. Radio Master Pajo. Radio Master is a PhD student in physics at the Department of Physical and Chemical Sciences at the University of L'Aquila, Italy. He is also having an MSc in physics, specialized in experimental physics of matter. His research activities focused on studying materials from fundamentals to applications. So please welcome Mr. Dario to share his views on this topic. Thank you so much.
Hi, thank you for having me. And now I share my presentation about it. So this must be good. So you see my screen, so I think it's good.
Yes,
sir?
Mr. Dari. Yes, Mr.
Okay,
Ayub.
so I can go. So as you already listen, I'm Dario Mastropolito, and I'm a PhD student in physics at the University of L'Aquila, and with my research group. Can I go, or there is some interruption? Okay, so with my research group, led by Professor Luca Ottaviano, we are investigating molybdenum disulfide, that is a quite interesting material, and we want to investigate the exciton-phonon interaction via controlled thermal annealing. Molybdenum disulfide, that is also known as MOS2, belong to transition metal dechalcogenide family that are van der Waals layered materials and are semiconductors. And the peculiarity of this material that is that are in a bulk phase, we have indirect gap semiconductor, but in the monolayer limit, so single layer of atoms, this kind of material begin direct gap semiconductor. So this is quite interesting to study because with this peculiarity, but we are also interested in optoelectronic and structural property of materials. And in particular, we are interested in excitons and phonon interaction, because excitons is a quasi-particle made by one electron and one hole, and this kind of quasi-particle can be visible in transition metal dechalcogenide, because they have very strong binding energy, and this is created by an impimping radiation when it is absorbed by the material and then is re-emitted by via radiativity photon emission. So we are interested in optoelectronic property because we can investigate directly the excitons, because we have optical and electronic property, because the electron is promoted from the valence band to the conduction band. And from the other side, we have phonon that bring a lot of information about the structural property of the material. And if there is an interaction between exciton and phonon, we can link directly the optoelectronic property with the structural property of our material. And as you can see from some papers on literature, we have evidence of exciton-phonon coupling or interaction in other transition metal dechalcogenide family of material, but not yet in molybdenum disulfide. So we want to investigate this because there is in literature some suggestion and indication that this kind of interaction can be present also in MOS2. And so this is the purpose of our investigation, to directly investigate the exciton-phonon coupling in a single layer of MOS2 by tuning the exciton intensity with 1 hour thermal annealing in air in the peculiar temperature range of annealing between 200 and 300 Celsius. And to do that, we use spatially resolved photoluminescence and resonant micro-Raman spectroscopy at room temperature with a resonant laser source. We want to do this kind of spectroscopy, photoluminescence and resonant micro-Raman, because the excitons can be detected by photoluminescence spectra, as you can see on the left side. We have two kind of excitons that are the A type. The A0 is a neutral one excitons, and the A minus is a charged one, charged negative excitons that is called a trion. And we use thermal annealing to enhance the exciton intensity, because we know from our previous study that an annealing temperature above 200 Celsius, we end up with enhancement of the photoluminescent intensity due to excitons. This is done by sulfur desorption from the plane of the MOS2 layer, and we can tune finally the photoluminescent intensity between 200 and 300 Celsius degree temperature. We cannot go further because an annealing at above 300 Celsius, with this type of annealing, we can start with the oxidation of MOS2, and this is not the purpose of our investigation. From the other side, as you can see on the right, we have from the literature resonant Raman spectra of MOS2, and we investigate the most interesting spectral region to directly investigate the phonon contribution due to first order and second order Raman modes. And these are due to vibration of the atoms in the layer. So this is an information about the phonon structure. So the first step of the study is the production of the monolayers of MOS2, and this can be done quite easily with mechanical exfoliation starting from the bulk material that is commercially available. And this is done by blue tape mechanical exfoliation. That is the famous mechanical exfoliation proposed by the Nobel Prize winner Noselov. So then when we have done the exfoliation, we pass to the deposition of the atomic layer on the silicon substrate with an oxide layer of silicon. And when the MOS2 is deposited on silicon substrate, we end up with a semiconductor with N-type doping due to the environment of the silicon substrate. Then the identification of the monolayer is made by using the optical microscopy and quantification of the optical contrast of the flake, and then with atomic force microscopy to check the stacking of the layer with respect to the substrate. And the sure that we are in the monolayer phase is provided by the check of the photoluminescence spectra. On the left, you can see photoluminescence spectra of a same flake of same monolayer of MOS2 before and after the annealing at 250 Celsius. I remember that the old spectra are acquired and at room temperature. The annealing is done at this temperature between 200 and 300. The sure that we are in the monolayer phase is given by the photoluminescence spectra because we have only a contribution between 650 and 700 nanometer, and there are no other peak due to indirect optical transition that are present in the bilayer phase and the bulk phase. So the decomposition of the spectra is made by the convolution with the Lorentzian function. we identify the neutral excitons and the trion excitons, as you can see. And there is an enhancement of intensity of both the exciton contribution. On the right side, you can see the correspectivity resonant Raman spectra of the same monolayer acquired before the annealing, so is the exfoliated, and after annealing at 250 degrees. And the convolution of the spectra is done by using a Voigt function corresponding to the peculiar spectral feature of MOES2 in this spectral region, with first order Raman mode and the second order Raman mode due to two phonon contribution of the vibration of our material. As you can see, also in this spectra, we have an enhancement of the intensity of the spectra, so, because that are normalized to the same acquisition time to compare the enhancement of the intensity. And to quantify this enhancement of intensity, we have defined the photoluminescent intensity ratio and the Raman intensity ratio. The photoluminescent intensity ratio is the total intensity acquired in the post-annealing spectrum, normalized to the same on the intensity acquired in the exfoliated spectrum of the same flake. So this gives us a quantification of the enhancement of intensity on the photoluminescence spectrum. From the other side, we have Raman intensity ratio defined in the same way. So the total intensity acquired in the post-annealing spectrum normalized to the exfoliated one acquired on the same monolayer. So this gives us a quantification of the Raman response enhancement of the signal. And as you can see from this figure, we have reported the Raman intensity ratio and the Fiel intensity ratio as function of annealing temperature, and the data are respective to different samples annealed at different temperature, between 200 and 300 degrees. As you can see, we have an enhancement of both Raman and photoluminescent intensity with superimposing trend up to 4 times for the 300 temperature of annealing. The first step, I'm interested in the 200 and 220 temperature range. There is a reduction of the intensity. This is due to the lowering of the monolayer with respect to the substrate with the thermal annealing, because with this process we have at high temperature we remove all the contamination and the impurity present due to the production method, and then at 225 degrees of annealing we start with enhancement, and this is due to the sulfur desorption from the basal plane of the material. And as you can see in the inset of the figure, we have done the R test to highlight the correlation between photoluminescence enhancement and Raman enhancement of the signal. As you can see, there is a one-to-one correlation with the calculated Pearson coefficient equal to 1. So this gives us a very strong information about the intensity enhancement, and this give us an indication and an evidence of the direct exciton phonon interaction between excitons and phonon, because we have triggered the exciton intensity with thermal annealing. And correspectivity, we have observed an enhancement of Raman intensity. So this is this proved the interaction, and this is direct because we have one-to-one correlation. And from our investigation, we have noticed also that in the spectra of Raman contribution, we have only one peak feature, that is the A1G, that is the green one, and that you can see in the spectra, that have which have out of plane symmetry vibration. And this peculiar peak feature is the only one that not manifest an enhancement of the intensity from our analysis. So we have moved further because the other all the other peak features have in-plane symmetry vibration. So we have also checked the symmetry dependency of this type of interaction. And as you can see in this figure, we have correlated the first order Raman modes with in-plane symmetry, that is the black one, considering the enhancement of the single peak with respect to the after annealing, normalized to the intensity acquired in the exfoliated one. And from for the other one, that is that have out of plane symmetry, that is the A1G. So it's the red one. As you can see, there is no correlation between the enhancement of intensity of this peak and the photoluminescent intensity ratio. The other one, the black one, have in-plane symmetry, and this is first order Raman modes, and manifest a very strong enhancement of intensity up to 40 times with photoluminescent intensity ratio enhancement. This gives us a strong indication that indicate exclusive in-plane symmetry interaction between excitons of A type and phonon with in-plane symmetry. So this is an exclusive symmetry-dependent interaction. And to go even further, we also analyzed the behavior of the neutral excitons and the trion excitons with annealing temperature. As you can see, we start from a contribution made preventively by the trion contribution for the annealing at 200 degrees, and we end up with enhancement of the neutral component with respect to the charged one component up to 300 Celsius of annealing temperature with inversion of the population. So this is quite an interesting behavior because with the trion contribution, we also have the information of the doping of our material, because we can use the two-dimensional mass action model specifically developed for the MOS2, considering the relativity effectivity mass of all and electrons, and from the information of the photoluminescence spectral weight of the trion contribution with respect to the total contribution of the both excitons, we can estimate also the electron density of our material and the evolution with annealing temperature. As you can see on the right side of the slide, we have the electron density of the doping of our material with, as function of annealing temperature, and we end up with reduction of the doping of our material but a slight reduction because we have a very slow magnitude of doping concentration, as you can see. This is not a high doping regime, heavy doping regime. So to conclude my presentation, I summarize the main result of our investigation. We have demonstrated facile and controllable few layer exfoliation and single layer exfoliation of MOES2, and we investigated the photoluminescence and resonant Raman spectroscopy, and we end up with an enhancement up to 4 times for both photoluminescence and Raman signals due to thermal annealing. We provide of the literature the first experimental evidence of the direct exciton-phonon coupling in 2-dimensional MOES2, and we also prove that this kind of interaction is highly symmetry dependent with exclusive in-plane coupling between excitons and phonon. We have also studied the evolution of excitons, neutral excitons, and trion with annealing temperature. And we also proved that thermal annealing can be used for tuning the doping of 2-dimensional MOES2. And this gives us also an indication and a suggestion that this type of process can be used also for other transition metal dechalcogenide materials, and also even to different van der Waals layered structure materials. So I thank you for your attention. I think this is the main contribution of our investigation. So I thank you. Now, if you have any questions, you can ask. I go then with the total screen.
Yes, thank you so much, Mr. Rairo Mastropolo, for this amazing and wonderful presentation. So here are the questions from the participants. So I'd like to, so from Mohammed Farhan Nazir, what if the size of MOES2 shoot is reduced to QD such that red pale emission becomes blue emission around 400 to 500 nanometers? Then what changes in exciton-phonon coupling can be expected?
This is quite an interesting question, because as you can see from my presentation, we have used a resonant laser source. That is a red one. Probably I can also show, no, because there is a, we have used a resonant laser source. This is a red one. The blue emission, the red for the emission become blue emission around the change for the. You can done also investigation of other excitation with different laser source. One our previous investigation is made by green laser that is around 532 nanometer. But we are now currently analyzing the data, because this is we want to use the resonant laser source. That is the red one, because it's resonance with the gap of the material. In this condition, we have an enhancement of the Raman intensity, because we are in a resonant Raman contribution. If you done the investigation with other laser source, maybe you can use also ultraviolet laser source. We have not the resonant condition, so we can also check the exciton-phonon coupling, but I not expect an enhancement of coupling that is quite big that in this case. So we have in a resonant condition the direct coupling of exciton and phonon. For other laser source, I expect not a one-to-one correlation, but a reduction of the coupling. So this is to answer the first question. So, and probably if you use not the monolayer of MOES2, or you done the, for example, an investigation on the bilayer of MOES2, you probably end up with a coupling between also with the indirect. Sorry, but with the out of plane coupling between excitons and phonon. But this is very low because the excitons have in-plane symmetry, and this is exclusive. There are very strong evidence in the literature that excitons of A-type have in-plane symmetry. So with the bilayer, we have we can expect very low coupling between phonon of the out of plane symmetry and excitons. To answer the second questions, is there a possibility to use the two-layer material in transistor application? How to reach in future collaboration with possible? This is quite an interesting suggestion because obviously you can end up with heterostructure. You can use MOES2 because it's a direct gap semiconductor in the monolayer phase. So you can create unique heterostructure between, I don't know, MOES2 and conduction with the metal or metal oxide. In the literature, there is some application to do MOSFET. So we have in literature they have already done some transistors. So this is a possible collaboration in the future. And the later questions is it possible to deposit MOES2 thin film using spray pyrolysis techniques? Honestly, I don't know this kind of technique, but as I can suggest, there is a lot of production method of MOES2 or transition metal decalcogenide, because the proposed one by us is a very simple way. We start from bulk material and with mechanical exfoliation, this is quite easy to do. But this is a top-down approach. You can use a bottom-up approach that is chemical vapor deposition. So you start from some precursor of molybdenum and sulfur from the other side, and with the chemical vapor deposition on the same substrate, for example, or made by silicon, you can end up with very high quality monolayer of MOES2. This is quite an interesting production method, but this is very difficult to do because you have to have chemical vapor deposition instrumentation, so sputtering and very high temperature to do that, because if I don't remember wrong, you need about 700 Celsius of temperature to do the synthesis of and the deposition of the MOS2 on some substrate. So I think what's this? There is another. You're welcome for the questions, and there is another questions. What is the thickness of the MOS2 layer? Maybe you. The MOS2 layer, the monolayer have 0.65 nanometer, but when you deposit on silicon substrate, you end up with different thickness, because you have also impurity, and there is a stacking between the layer and the substrate. But the check of the monolayer phase is made by photoluminescence spectra, because we are sure that monolayer have a direct gap, is a direct gap semiconductor, so we have direct optical transition. In the bilayer phase, even at the bilayer phase, you have indirect optical transition, and in the photoluminescence spectra, you can see other peculiar feature of on the spectra. But the thickness of the monolayer, the freestanding in isolated way, is 0.65 nanometer. But in the deposition, we have a thickness, a major thickness due to the substrate. So I think there is no other questions about that. Yes, the Raman, there is the problem of the resonance, yes, because in the green and the blue, with the green and blue laser, we have not the resonant condition with the gap, because the gap of this monolayer of MOS2 is about 2 electron volt, and the laser with the red source is about 1.96 electron volt. If you use a blue one or a green one, or even an ultraviolet laser, you have a much bigger energy, so you are not in resonant condition. And in the Raman spectra, you have different behavior. You cannot check, for example, the second order Raman peak. You can only check the first order. So this is another investigation, but this is a further suggestion for another investigation. And also we are looking in this direction, obviously, to also check other exciton-phonon interaction, and to even more deeply understand this kind of interaction. That is quite interesting, because link directly the optoelectronic property and the structural property of our material. So this is quite interesting for the engineering of transition metal dechalcogenide, for example. So if there is no other questions, you're welcome. The presentation.
Thank you so much, Mr. Radio Mastery Pojo, for this amazing presentation. And any further more questions, so I will contact you via email so that you will please do answer them all. Thank you so much once
Okay,
again.
thank you. Thank you, you too.
Yeah. So now, without further delay, I would like to introduce our next speaker, Professor Jainstein. Professor Jainstein is the founder and CEO and chief design Albert Einstein researcher of two startups in USA. I'm not sure that I abbreviated it correctly. He refers to Albert Einstein, but let's discuss something new from his presentation. And he's a senior unified communications engineer, Microsoft Corporation, Redmond, Washington, and he's a senior telecommunication engineer at Winco next of Paderborn, Germany. So please welcome Professor Jainstein to share his thoughts on his presentation, wonderful presentation.
Hello, everybody. Thanks for joining this conference today. Maybe it's the last one. And I hope to present many innovations today. So it's the last presentation today, but I need your mind so open. So the presentation is about A-sphere. A-sphere is a concept about the next nanoprocessor, and it's not based in mind. It's based on heart, or heart works. So to discover that, I travel around the interior America, living with different tribes right there, not also with Native Americans, but also in South America, to discover what is the ether. Ether is the major secret in the vacuum. And starting from this concept of ether, we can discover what is the vacuum, but also what is the everything. Because when ether vibrates, this generates the materia, and also we can see the energy. So for me, from my special point of view of the future, zero R evolution is the next step in the technology industry based on this. So yes, I'm founder, CEO, and also chief design research into startups in USA. First, an academy in California, in Silicon Valley, after my background in Microsoft Corporation, also in Winco in Europe. And the last adventure that I had is Jamestown LLC in Arizona, because I think that Arizona is the next Silicon Valley, but with another name, Graphene Valley. So it's the place about the superconductors. So semiconductors era is dead. It's close to be expired, because the fusion, we cannot reduce the volume of the chipset right now. So this is the reason why I say it's close to expire. So the computers that we know in the current times are not valid for the future. We have to design another different way based on graphene and superconductors. So electricity or electronic chipset is not the future. The future is based on electromagnetism. And this is the key. Not only graphene and superconductors, but also how the new processors works. So to understand this new way, I have to deep dive in quantum mechanics. And yes, I'm very close to the Albert Einstein ideas about this is the wrong way, because in the last century, we investigate about how to solve a lot of issues that quantum mechanics cannot solve. So I deep dive and deep dive and deep dive about what is the source of all the problems, because maybe it's only one, and it's quantum mechanics. So quantum mechanics is the problem itself. And for that, the first beginning is the Planck constant in another different way. So all the material right here is property, is intellectual property of Einstein LLC. So let's start. Agenda. What is the new concept of the equation with the Max constant dielectric constant in the entire spectrum of energy? Ether covers the visible world and also the invisible world, both sides. And to cover this, we have to change our mind. With this new equation, we can create a new device, a sphere, and apply the algorithm and using graphene to conduct the electrons around the sphere. So this is the core of this presentation. And to understand the algorithm, because it's secret, I want to explain 3 different categories: energy, frequency, and vibration. This is the 3 components of the new equation of entire spectrum of energy. And I use some important mathematical discoveries in the history, like Archimedes, Pythagoras, and also Euler. And I create 3 rules. The first is for energy is Einstein-Hans rule. The second one is Einstein 369 rule. And the last one is Einstein zero harmonics rule. So let's start from the equation. The entire spectrum of energy equals to harmonic orbit of the multiverse multiplied by the field force. And the meaning of the field force is the frequency of the ether. Why I'm using multiverse, not universe? Because everything is creating from frequencies. So like our brain is like a radio synchronized with different frequencies of the universe. So if we have different frequencies, we have not only one universe. This is the question about the multiverse. And why the H is in capital ones? Because this is like a cycle. So time is not linear, time is circular. And it's a dielectric component. So anytime that we have one spin in this circle, we have a positive or a negative value. So like Dirac constant is the half of Planck constant. H in capital 1 is the double. So it's the plus 2 minus Planck constant. This is the Einstein constant. Frequency. So I'm speaking about the frequency of the ether. What is the value of n? So n is the vibration of the ether. So it's directly proportional to the frequency. If you want to increase the frequency, you have to push more vibration in the ether. And if the ether has no vibration, there are no frequency. This is the vacuum, the architect, the structure of the vacuum. So the algorithm increases to how the sphere grows with these three terms: energy, frequency, and vibration. Well, A0 R evolution is the next step in the technology from quantum computing. And for that, we need a new theory, because for me, quantum mechanics is not the solution. And ether is the key to solve this, applied to the sphere. So let's try to understand the sphere. Energy is always contained in a volume, and the transformation of this soul node generates losses. The zero dimension of ether is where the fundamental volume is invisible to the human being eyes. Energy is visible when ether vibrates and never can be destroyed but transformed. So, a sphere represents a structure in equilibrium or balance that is capable of modifying its volumes to automatically generate energy with the vibration at itself. So this is the key of how we can see the energy. What is covered by an algorithm with these three concepts: energy using a fusion with a spiral. Frequency is based on fission with triangulation. And vibration is the result of pure arc, and I'm using exponentiation. All this information is covered by maths, physics, geometric, and also the spiritual world. So benefits about using graphene with a sphere. The implementation of algorithm in the sphere produce three values, no two, because we are speaking about electromagnetism, no electrical one. So it's not a bit, it's a nanobit. And the three values is positive, negative, and the neutral one. And this is the beginning of the logical procedures of nanoprocessors. We have no overheating because we never use resistance at all, only superconductors and electricity in different positions of the new dimensional coordinate system reproduce the positive, negative of the neutral, but not with resistance. And maybe this is the crazy way for the new pioneers, I don't know. Who knows? This is the representation of the sphere in a concept of 6-dimensional coordinate system. Top and down, we have 2 layers of graphene, and in the middle, the sphere with the 3 rules applied, and with the algorithm also. So let's discover. Let's start energy. Archimedes has one of the major secrets in this new theory. So imagine a cylinder, and a sphere, and also a cone. So if we split these 3 figures in the middle, we discovered that with the same circle in the middle are compatible. So one cylinder is equals to the hemisphere and with the middle of the cone or a little cone. So let's see the stream of the slide. The cylinder of both cones. So it's the same figure, but with the ring in the middle. So if in an energy cylinder, we ring the middle, we create an sphere. And this volume is the same. So transforming the volume, we transforming also the energy without losses. This is how a sphere works and how creates vibration without any loss of energy. The cylinder represents the Einstein constant because it's the dielectric heartbeat. In the right, we have a magnetic dipole because we are using the magnetic property. And in the middle, we have both the dielectric with the magnetic dipole, but with a rule to create the harmonic frequency in both sides, in both directions. The ether can be represented through two graphene layers, top and down, in which a dielectric and magnetic dipole are in the sphere. Obviously, we have to use the algorithm in order to create the feed force inside of the sphere. And one of the first rule applied in the energy is the Hans rule. The Hans rule, look at the 3 fingers. If we use the classical right hand rule or left hand rule, Fleming rule, is because we are using the 3D or the XYZ coordinate system. But it's limited because C is the last letter. So I cannot reproduce how it works in higher dimensions with this system. For that, I create another one. And it's not based in the right hand and the Fleming rule of the hands, but also the Einstein ether hands rule. So the secret is the center of the cylinder. Depending of the magnetic dipole, we can expand or shrink the center of the cylinder. And when this happens, the first finger is the feed force and the second finger is the magnetic dipole. So when we join together, what we are doing is reproduce the movement of the electron with more and more and more intensity outside the surface of the sphere. So these are represented by the other 3 fingers, 4th, 5th, and 6th dimension. Why 2 hands? Because we have 2 different spins. So the top layer is turning to the left, so it's anti-clockwise, and the left hand is down, is the representation of the negative pole, and is rotating, or the spin is clockwise. But in the middle, in the center of the cylinder, or in the center of the sphere, are both hands working together. And this is how works the heartbeat of the multiverse. So hydrogen works something like this. So it's like a torus There are a lot of draws in internet about how, in fact, a black hole could works, but I'm speaking about the center. Is for me is the shape is a sphere. Frequency. This symbol is very curious because I found in a temple in Egypt. It's like a eagle face also with two eyes and the beak down. And what apply here is Pythagoras theorem. So we can find two triangles, one on top, one down, with a rectangular triangle, and the green part is the frequency top and down, but it's the harmonic frequency because it's the same side, the same length in the both sides. This is the reason why I'm using a plus to minus in the both values, but one is red and another is blue, because one is visible for our eyes, or the red one, and another is invisible for our eyes, the blue one, but both exist at the same time. And anytime that the frequency push in the surface of the sphere, causing not only the increasing of the volume, but also the visible of this sphere. It's like day and night. So the day could be the red side and the night could be the blue side, but both exist at the same time. So this is the best definition of the harmonic frequency in two directions of the sphere. And the values are root square of this new concept. And this is a new concept of a number to represent this new kind of frequency. What is time here? Because we are only using the vibration of the ether. Well, the time is the dielectric constant in the entire spectrum of energy. So it's outside the F value. Let's see the positive ion quantum. Ion quantum is one of the part in red. So is the top one is the layer on the top of graphene affecting to the sphere, and in the down we have the same but in another direction. Anytime that we increase the frequency, what is happening with the Pythagoras theorem is that we are creating a spiral of Theodorus without any increase of one of the sides, because this is the fundamental volume of the ether. And there are two reasons why one of the direction is the frequency is straight, in a straight line, and another is around the point, the final point of the frequency, because it's the electron rotating. And this depends of the magnetic dipole. So when we have, when electron is present with a magnetic field, the electron rotates. But when we have no magnetic field, the electron goes straight. So this is the difference between the straight lines and the fundamental volume around any of this point of the frequency. So in the frequency, the rule is Einstein 369 rule. I split the circle in 6 parts, 6 on the top and 6 down, like a mirror. And if you take the values of the angles, because any partition or any portion of this circle is based on 30 degrees angles, we can see that 30, if we assume 3, 0 is 3, 6, 0 is 6, 9, 0 is 6, 9 plus 2 plus 0 is 3, 1 plus 5 plus 0 is 6, 1 plus 8 plus 0 is 8. So all the time is 3, 6, 9, 3, 6, 9, 3, 6, 9. What happens if we assume the vertical ones? We discover that 3 plus 6 is 9. What happens if we assume the horizontal ones? 3 plus 6 is 9 also. And what happens in the diagonal ones? If we multiply the values, is 9 also. So 3 multiplied by 3 is 9. So this is the secret of balance, 9, the number 9. And this new concept of 6 dimension is in balance also. And I'm using this in order to recreate the model of the sphere. This is the electron going in the direction of the top layer of graphene from the top to the down, and the circles 1, 2, 3, 4, 5, 6 in red are the frequency, and in blue ones are the harmonic frequency, because it's the same but in another direction. And the circles around are the trajectory of the electron anytime that we have a magnetic field. Vibration. So Euler is what I use to reproduce in the 6th dimension all this concept of rotation to create the spin. So in the top hemisphere of the E sphere is the spin is up, and in the bottom hemisphere of the A sphere is down always. So this is the 2 of the 3 values of the nano bit, positive and negative, and it's according to the spin of the electron around the sphere. And how works or what is the trajectory of the electron when we have the presence of magnetic field? Well, to do that, inside in the core, in the fundamental volume, I'm using the lemniscate of Bernoulli. This is the secret about how is the trajectory of the electron inside. And any time that is going to the stream of both directions are creating the vibration outside. So it's the surface of the sphere outside, but inside this is the trajectory of the electron. This is the both cones creating the 0 point of energy in the center, and then this is the vibration outside, and part of the algorithm is included in the left. This is another representation of the harmonic frequency. You can see anytime that the electron going in both directions. We have two different shapes, an ellipse outside and also lemniscate inside. And this is the reproduction of the fundamental volume in any dimension, any plane of the sphere. So the difference between a sphere and the A sphere is that the A sphere is growing and the classical sphere is static, so it's not growing. Well, I'm publishing this in 3 books. The first it was published last year, and I presented in Los Angeles in November of the last year. Is ready. It's available in Amazon. I'm working in the extended and the last one the next year to create all this information in an entry trilogy to include all the technical details about that. And also one of the goals is reproduce this in a lab to create the sphere as a device. So thanks. I don't know if you are so tired or I'm very clear during my presentation, but I'm open to any question you have. Thank you.
Thank you very much, Professor Jainstein, for this amazing presentation.
You're welcome.
Yeah, so we just got to move on to the audience. So we have a query from Mohammed Farhan Nazay. Does multi-universe exist as a physical reality? Thought it may be quantumistic probability. Why and how people came to this thought?
Well, practice meditation every day. So I'm a theoretical scientist. We have a lot of evidence. For example, the lemniscate is the movement of the moon and the sun. So if we establish one point on the Earth and with a camera, and we take a picture in the same time, all the days during 1 month, we discover that the moon and the Earth is moving like an infinity. And if we do this exercise in the entire year, we can see that the sun and the Earth is also dancing together in an infinity shape. So all this information are concept and are based also in the background that I have, because I was unified communication engineers in different companies. So I study a lot of physics during last decade. And I'm thinking about, and this is a reverse engineering. So maybe wisdom is a memory of the past times, but I think that innovation is a memory of the future times. So our brain is like a radio, and we can connect with different frequencies. And for me, time is not linear, time is circular. So I don't know if I live in the future in the same way that I don't know if I have another lives in the past. But I think that when you have some feelings about things that could be or could work, it happens. This is the magical of the dream. So imagination, like Albert Einstein said, is so powerful. And for me, we have a limited vision of the reality, only when our eyes are open. But right here in the audience, there are a lot of people from India that practice meditation every day. And when we close our eyes, we can feel another things. I think that this is the place where we connect with what we call God, or the central energy of the multiverse, and our heart. And from this point, we can imagine everything, and this is the seed of the material world. So a thought could be reality in the future, and maybe this is a dream, I don't know, but future is the answer. More
Thank you so
questions?
much. Yeah, and here is one more question. Do you think the dimensions are somehow aligned with the fact of the Earth we see every day?
Yeah, I think so. Yes. All this information that I shared today is how our energy field works. So when I'm speaking about 0 point of energy, or the central point of the sphere, this is our heart. Is the central chakra, is the fourth chakra. And the surface of the sphere is our aura, is the limit of our energy field. It's very curious that our nervous system works with 1.5 volt, so it's the electrical part. But our heart chakra works with magnetic field, and is incredible when you use your magnetic power of your heart to create things. So it's your dreams. And when we use the coherence between your mind and your heart, so your electric part of your body, of your energy body, and also your magnetic part from your heart chakra, both working together, you are in balance and you create your dreams in your material world. So I'm thinking I will reproduce the EMF, or the electromagnetic field of the human being in a machine or in quantum computing, because this is a balanced way of the energy. If we use only the electrical part, so maybe from the discoveries of Nikola Tesla, we destroy the balance with the electricity, because we are extracting the electron from the atom. This is not the balance in the nature. The nature works in another way. So my ideas is about this. It's about recover the balance in the future devices. And our body is the perfect machine. So in fact, we don't need vaccines. We don't need drugs. We don't need anything more than control our mind and control our emotions to be healthy. So why not we can use this magical way of energy use in our body to put in the future devices. This is my vision. More
And
questions?
here is one more question from Abdi Narifogi. Are you connected to or concerned by the Resonance Science Foundation led by Nazim Haramain?
No, I have information about him, and also in the last year about the Herb Math in California. It's another institution that study how our heart works. But I never worked with any of these organizations, because I'm traveling my own journey. And I'm open to collaborate with different organizations. I'm looking for partners, collaborators, investors, because I think that this is the close future, because we have to solve a lot of things. And my first idea, it was conclude the theory and then apply, but I'm open to continue this journey with anybody that has the similar ideas.
Thank you so much, Professor Jainstein, for your response to the audience.
Thank you.
For this amazing presentation as well. Thank you so much for sharing your thoughts.
Thank you, everyone.
So, and now I would like to go to the next speaker. So, Professor Randy van der Waal. So, Professor Randy van der Waal is not alive right now, so he has sent his recorded presentation video to display it. So, Randy van der Waal is a professor, energy and mineral engineering, material science, and engineering department of energy and mineral engineering, Penn State University. His current research interests include chemical vapor deposition and flame synthesis of carbon nanomaterials, where application as conducting thin films, fundamentals of graphene bonding, carbon graphitization kinetics, carbon material characterization by high resolution electron microscopy, HRM with image quantification for nanostructure, electron spectroscopic techniques, spears and doublets for bonding detail and carbon materials oxidation reactivity dependence on nanostructure. The optical, electrical, and thermal properties of graphene and other graphitic carbon forms produced by pulsar laser heating is presently under study, as is the fabrication of advanced carbon-carbon composites based on this. Related study includes Baker. And now I would like to share his recorded video presentation.
Good afternoon. My name is Randy van der Waal, and I'll be talking about laser annealing of carbon. And I'd like to acknowledge Drs. Joe Abrahamson and Madhu Singh, former graduate students, for their efforts in this work that I'll be presenting. Just briefly, by way of introduction, some of the work that my group does is very carbon focused with regards to understanding the structural transformations of carbon. As a function of heat treatment temperature, we use novel treatment processes such as laser-induced annealing or graphitization. We also focus on novel synthesis methods such as flame synthesis for carbon nanotubes. And also, with all those forms of carbon, perform characterization primarily through electron microscopy and spectroscopy methods. Briefly, I'll just provide a little bit of introduction for carbon materials, talk a little bit about their transformation and our experimental results. Now, carbon materials in general have very high mechanical properties, being far lighter than steel and yet with very high strength. In particular, carbon materials, carbon composites in particular, are known for their ductility, hardness, elasticity, and fracture toughness. Many of these materials have found use as thermal shielding materials and or as structural materials, such as in engine components and primarily, especially these days, aircraft brakes. As I mentioned, carbon as a material has many special properties, in particular, a very high melting point, is very stable to very high temperatures under vacuum or inert environments, and even under non-reactive, under air conditions, it is non-reactive up to 800 degrees C, and it forms carbides with many other transition metals. In terms of the historical progression, we have seen over the last decades the transition from 0 to 1D to 2D from the 80s through the 2000s. And the question is, what about 3D? Well, there have been development efforts to produce 3D architectures of carbon, namely such as by Professor Dye at Case Western, where they used graphene sheets with iron catalyst to form carbon nanotubes, although the reality is that the composite as made was still high in iron content, very different in structure than the idealized model as shown here. But nonetheless, making advanced carbon materials and hierarchical constructions of such has been of increasing interest, such as, for example, in this highlighted article by CNE News for carbon fiber 3D printing graphene materials for structural composites. And at a different conference, 3D printing of carbon allotropes was in fact an entire session. Just by way of background, Penn State itself does have a Center for Innovative Materials Processing, otherwise known as CIMP 3D. These are just some of the illustrations. It does have all the commercial scale instrumentation, fabrication methods available at the facility. In particular, one of the methods is selective laser sintering, SLS as it may be known. I'll describe a little bit about that, but this is just showing some of the versatility of the hierarchical construction that this technique by laser annealing of powder can achieve to produce three-dimensional forms. Effectively, how the technique works is to have a high intensity laser annealing layers of powder that then build up a 3D architecture with each new layer in a prescribed format, building up layer by layer with a refresh from the powder bed to as the feedstock for each new layer. Now, carbon as material or the high temperature stability also presents a manufacturing challenge from the standpoint of the high temperatures required, number one, and secondly, the graphitization kinetics, at least for what has been known, have been very slow. Namely, the timescales for graphitization, given the high temperatures that have been required, has been characterized, measured over the timescale of either hours or, well, hundreds to thousands of minutes, but certainly these timescales are not commensurate with what one would need for 3D printing or manufacturing. And consistent with that, one would ideally like to be able to construct models in terms of the energy in, energy out, in terms of an energy balance formalism, such as the schematic of this picture as it shows for absorption, conduction, vaporization, all the energy terms in balance by which one could then calculate the time evolution of the temperature of the material to then evaluate sintering and or annealing of the carbon itself. But even then, as has been studied over many decades, many other processes can occur, not just with metal particles per se, but also with carbon, such as surface ablation, fragmentation, coalescence, etc. So even if one were to perform or calculate in a steady state energy balance in this formalism, many other ancillary processes might yet occur. So that brings us to our fundamental studies to test the capability or facility of laser annealing, either using a pulsed or CW laser to sinter and or anneal carbon materials towards ultimately perhaps 3D manufacture using them as feedstocks. Allotropes themselves are very natural then feedstocks for their powder nature in analogy with metal powders today. So the first laser that we utilized was a pulsed neodymium YAG, Q-switched neodymium YAG, very, very high temperature heating rates, for example. The schematic of the optical delivery in beamline is shown here, but basically under inert conditions or could be in vacuum, we can deliver pulsed laser light to the sample. And that's just illustrating a picture, a burn pattern of the laser beam spot on the sample, showing some of the apparatus as used for some of the tests, this being one of the environmentally controlled chamber for smaller scale tests with available pumping apparatus as well. Alternatively, as I may mention, we have tested a continuous wave CO2 laser Again, fantastically high heating rates, also capable of achieving graphitization temperatures, similar optical delivery system. Again, just showing a picture of some of the apparatus required in our laboratory for these measurements, either using a YAG, this is showing some of the optical delivery system, vacuum controlled system, or in the case of the CO2, some of the beam delivery optics shown here. And then often these measurements were performed under atmospheric pressure, but with an inert shroud as delivered by a plenum. This is just the plenum. Often smaller samples might be contained on that plenum. These two movies are just to illustrate some of the laser heating, just for your edification. That's showing the pulsed neodymium YAG. This movie is showing you the CO2 laser heating. We can vary the energy and the time for the CO2 laser and the time at temperature. So let me just give you a couple other details for the experimental matrix here. We used a carbon powder, a commercial and powder of carbon black, R250 made by Cabot, and we could characterize by our TM analysis quantified for lamella growth reorientation and tortuosity. So we could characterize the laser annealing as a function of pulse energy and pulse number, or number of pulses. This is just illustrating that we also are able, through optical pyrometry, to measure, capture in time, the temperature of the carbon as it is heated and cooling thereafter by the laser by applying Planck's radiation law to the blackbody emission observed. And dependent upon the powder carbon or particle size, such as illustrated here, there are vastly different timescales for the cooling after cessation of the laser heating. So we can track temperature and monitor it in time. This is just showing a TM image of one of the carbon aggregates of the carbon black. This is part of the LaCie grid on which it is supported. Particle size, the fractal aggregate itself, and the laser annealed form. And you can see that the morphology is retained. That's good. But there's also considerable internal structural change, annealing, as it may be called, associated with the high temperatures to which the carbon has been heated by the pulsed laser action, illustrated by the red arrow. But the aggregates may remain intact. That's useful. The primary particle sizes remain the same. That's very useful for designing materials that would be constructed using a powder. You do not want necessarily extreme shrinkage, for example, nor perhaps even expansion of your part as you're trying to fabricate it. That would very much complicate your fabrication. But nonetheless, as I may mention, you can see the internal structural transformation, which here, as shown, is very dependent upon the number of pulses that have heated the carbon. And as I made mention, we have developed fringe analysis algorithms for quantifying the nanostructure in these TEM images. We can quantify lamella length, tortuosity, separation distance, and represent those metrics of nanostructure by statistical representations, i.e. histograms, as shown here for fringe length and tortuosity. And so Oberlin, back in 1984, had developed this conceptual model for the graphitization stages of a graphitizing carbon with different levels or lengths scales applicable at different temperature stages. Somewhat analogously, we can measure and quantify fringe length, track their convergence to an asymptotic value. We've also applied EELS measurement, electron energy loss spectroscopy, in the TEM instrument to measure the ratio of sp3 to sp2 carbon, and again, either as a function of time above temperature or as a function of the temperature itself to which the carbon has been heated by the laser, we can track the evolution and growth and convergence of sp2 fraction of the carbon and the conversion then from sp3. So in terms of overall research findings, this is a relatively short talk, but I hope I have demonstrated laser-induced heating as a potential tool for carbon bonding. The likelihood of applying this to allotropes will very much depend upon the chemical composition of the allotrope. In particular, for example, graphene oxide with high oxygen content undergoes, well, considerable gasification upon temperature elevation. We chose here, beneficially, carbon black with minimal heteroatom content, and hence particle size analogy was maintained. The only structural transformation was that internal not external. Results here support a three-fold hypothesis. This was part of the theses that I made mention of before. But laser annealing at nanosecond timescales retains particle size morphology. We have, in conjunction with Dr. Van Duyn here at Penn State, performed atomistic simulations that do indeed support bonding structural differences on these different timescales by these different laser heating methods. But we believe certainly the laser processing itself would be very applicable to thin film processing and related applications such as layer by layer buildup in selective laser sintering. And with that, I'd like to acknowledge support through the Material Research Center per se, and thank you for your interest.
And I would like to thank Professor Hello. Yeah, I would like to thank Professor Randy Wonderworld. So, however, he's not live, but he send his recorded presentation video. Thank you very much once again. And I would like to pass over this to Dr. Nagaraja Survedevara to conclude the day today.
Once again, good evening and almost a good night for somebody like me. It's almost midnight, 12 p.m. The day one of this conference on the November 25th, which almost there is a 17 speakers were there. Out of the 17 speakers, 4 keynote speakers, followed by the rest of all from the various parts of the globe, from the Morocco, United Kingdom, the professors from the Russia, India, Australia, Ukraine, South Korea, Spain, Sweden, Malaysia, it's me, then Ireland, Iraq, Italy, USA. So far, this many countries were represented today. From the United Research Forum, we take this opportunity to thank really the professors from the various parts of the globe, the young researchers throughout the globe who take this time to spend your valuable time. And we believe that you gain a wonderful knowledge in the day one, the same expecting to be continued for the tomorrow. One and all, take this time, rest for a while. Maybe 6 hours of sleep might be, have a good sleep for you guys. Thanks to the professor, Dr. Usman, who is constantly observing since the morning.
Thank you very much. Good night.
Yeah. Thank you, Professor. I can see in the morning I was logging. Since morning, you are there constantly monitoring the sessions. We are from the part of the organizing team. Thank you, one and all. Have a good night and a good day. Bye-bye.
Yes, sorry. So we have a keynote presentation on day 2 so the day 2 begins on at 5 a.m. UK time and it ends on 15:45 London time, followed by the keynote presenter, Alexander V. Follow from Russia, followed by keynotes and some oral presenters and poster presenters. So, and I would like to specially thank the organizing members, Professor Alexander Soldatov, Professor Southern Federal University from Russia, and Professor Osman Arigulay from Fayat University from Turkey. And special thanks to Dr. Nagaraja Suryadevara for handling the rest of this session. And thank the audience for your patience and for your kind attention. And have a great day. Have a good morning or good afternoon or good evening, and have a good night. See you on tomorrow. Bye-bye.